All right, friends, let's get started. Good morning. I hope that you had a very wonderful time with the Ansys training. So I'm all ears. If you have any suggestions about the first 2 days training, if you want to tweak it a little bit for future events, this is really important. You can actually steer the future events, and we have been doing it. We have been listening to people, and then we are trying to accommodate whatever they are trying to ask. So today, actually, I changed the agenda a little bit, just the order, because I thought that we need more time with the hands-on session. So I pushed it to the after coffee session, because we will have more time. If you get stuck, I'll be able to help you. And I really want you to actually go through the entire tutorial. So even if it is trivial for you, just go through it. I'm pretty sure you will learn something. And if there are people, I know there are people who are actually really beginner with Shaheen, really beginner with Fluent. So just go through the entire tutorial with me. So what I'm going to do is that first, I will explain the consulting services. This is number one item. So I will explain what we are offering to our users. So I will explain CFD consulting for COUST students, COUST researchers, and in-kingdom users. So by the way, let me get confirmation. Can online audience confirm that they can hear me all right? Am I too loud for them?
Yeah, sure.
The sound is good.
Okay, thank you. So was yours. Okay, so then after that, I'm going to tell you, well, I'm asking you to do something extra to use Shaheen. You're fine in your world. I want to change your life, and you want something in return. So I have to convince you that what Shaheen, what HPC can offer you. So if you are convinced, then you'll go do the extra bit and transition your life and your workload. I believe there is no computer science person in the room. There is no SMC person, right? So all PSC or BSc, maybe. So I will do the extra bit, and I'll go into the basics, very, very basics of parallel computing. So you'll hear something about OpenMP, shared memory paradigm, distributed memory paradigm. Don't worry, no Fortran programming, no C coding, no Python, nothing. It's just a concept, because once you start using a supercomputer, you need to know at least that your code is threaded, your code is can exploit distributed memory computing or not. Is it MPI or not? If it is not, you'll be using all the nodes of Shaheen, and it's not going to do anything for you. And trust me, we have seen such users. So a little bit of basics over there, and there will be some exam questions on that. Not too much. So everything will be repeated in the class. So don't worry about exam. So it's just a learning process. After that, I'm going to take you to the simulation workflow. What is it? I think Ajay and Wasim did a very good job in explaining you the simulation workflow. Your life starts on your workstation, maybe in your lab. You see some geometry, you want to analyze, you measure it, you need to model it. And from there, you go through the meshing and boundary condition imposition, initialization, and then transition that input file. And that is true for all simulation workflows. Fluent, 𝐀𝐍𝐒, Converge, what else? COMSOL, OpenFOAM, everything is like that. You transition that thing on a supercomputer, then I'll tell you what extra needs to be done on a supercomputer, and then blah, you will get your solution file. Now you have two options over there. Either you visualize your solution on a supercomputer, but that's difficult because supercomputer will not allow you to open a GUI window. So you have to do things in a different way, a batch way. I think none of you is old enough to understand MS-DOS. Do you know what there was something called MS-DOS? Maybe Geo can. So I'm not saying anything about your age. So I know for sure. So even before Windows, the way you know Windows, you need to type something, you need to copy something, you need to go to a directory. So old people understand, new generation, you guys speak and you expect your computer to write code for you. So, well, we'll go through some of it, and then you bring your file back onto your on your workstation if it is not too big, and then visualize it, and then you're done. You make your engineering decision, and then you get your degree or whatever, or your salary. However, life is not that simple if your data is extremely big. So you're going to do a large eddy simulation of a full Formula One car. You have any idea how much of data you're going to spitting out on a supercomputer? Just give me a rough idea. 1 kilobyte, terabyte, of the order of few terabytes at least. If you are careful enough not to dump solution after every time step, so you need to wait for maybe 100 to 1,000 time steps, because we are looking at of the order of 100,000 time steps if you really want a truly turbulent flow. So you will be looking at huge amount of data. What you're going to do with that? You're going to copy, you'll copy and go on vacation and come back and still it will be copied. So it cannot be done. So you have to go and do something differently. So I believe we need to do a specialized training for that. How to handle of the order of petabyte data. That's the future. We will do something with that. Maybe we'll partner with our data science team. So they have some solutions and we can probably do. So then there is another. So towards after that, I have another. This is an example using a simple 3D cavity flow. Extremely simple. Nothing can be more simple than that. But I believe at least 50% of you will actually learn a lot from just simple example. So if you have more appetite, I have another test case where you will be doing a full CFD simulation on a sedan car. So you'll by the end of the session, you will see some pressure contours on the surface of sedan car. That's cool, right? And everything is prepared for you. It will probably take you 15 minutes if your fingers are not tied and you can type correctly. So with apologies, online friends will not be able to use Shaheen. Only people in the room will be able to use it. I promise next time when you'll be in person at 𝐀𝐿, you'll be able to do that. Instead, I will give you some hints what you can do. So I will tell you to reduce your problem size so that you can run your simulation on your workstation and then carry on with us. So I'll be careful when we have to digress. So so far so good. So this will take us to the lunch, and on the agenda you'll see a TKS event from 2 to 3. We have moved that, and Ajay and Rahul are actually giving them a training right now. So why I'm telling you, you guys are not TKS friends. So I'm just telling you that, well, there is some event that we are doing with students also. And the aim is that, well, simulation should not be that difficult. So it should be something that, I mean, 9th and grade kids, they play Minecraft. So you guys know Minecraft? Yes. Yeah. So they play Minecraft. So they have idea about geometry. So in fact, I was very surprised to see my 9th grade son actually do a Formula One geometry car. They do 3D printing. So then I said, well, they can do this thing. So why not put a box and do the simulation? So they are actually doing it right now. So that's a good idea. And even if this cavity flow is difficult for any one of you, we can merge that training with this training. So just to make it even more simpler, because why I'm not trying to offend you guys, because there are experimental people. So they do not want to know about discretization. They do not want to know much about boundary condition. They just want to get the results. So I see some slides. So I think I'm resonating. So I'll just try to give you a very easy solution for that. And there will not be any prize distribution or the certificate distribution, because I think it's unfair to give you guys certificate and have some tabs, and the online people are just getting an email. So in a hybrid event, I think it's more fair to just send email to everybody. So what essentially it means, we will all save some time. So we can say goodbye to each other at 12 after these lectures. And at 12:30, I will activate the exam link on the website. So the Holy Grail is keep going to website. 12:30, it will be activated. You start taking exam. You are free to stay here and do the exam here. And then, or you can do at a leisure of your office or home. And at 2 o'clock, the link will be deactivated. You will not be able to upload after that. So be careful about that. And at 2 o'clock, I do not want to get 100 emails. Could you please, please just do it a little faster. Is this clear? The agenda, what's going to happen in the next 3 hours? Any comment, any suggestion? If not, let's get started. The good thing is that I did not cram too much of material, so we have the leisure of going slow and talk to each other. Yeah, please.
So before we start, this material is available one more time. Where is this material available for today?
So right now, I have not uploaded it. So
okay.
After we will do it, I'll make it available.
Please.
Yes.
Okay, thank you.
You will get everything. Don't worry about that. Because
thank you.
I think, if the material is available, I think sometimes people, I mean, they're not more attentive. So I think for that also, I'll wait for your feedback. If you guys really want a material up front, then we can do that also. But you will get everything. Don't worry about that. Any other question?
Thank you.
Convergence or converge? Yeah, so sure. You can. Can you tell me the name of the person? He's a 𝐊𝐀 person? Okay, so we will discuss all these things. So with Converge, the issue is that you need to have license also. So commercial, so it's not having access to Shaheen doesn't solve every problem. You need to have license. So I'll go into a bit more detail. Since this is Ansys workshop, I don't want to talk about Converge that much. I'll explain you the Ansys service, and I can take on with 𝐊𝐀𝐔𝐒𝐒 offline. I think the issue with him is that, well, he does not have license, and he needs to have permission from 𝐊𝐀𝐔𝐒𝐿 to be added to Converge group, and then he will be able to run it. That's the answer to him. All right. I don't see okay, they are probably late. So this whole event was for them actually, but again, let's get started. So actually, I'm running a in-kingdom CFD consulting programs, and you're all part of it. And the idea behind this in-kingdom outreach is that, well, we need to align, 𝐊𝐀 need to align ourselves with what is happening in the kingdom. So we are offering our services to Saudi universities and Saudi industry. So I'll go very quickly on that. And in the process, you will understand how you can access Shaheen. How many of you have a Shaheen account? Okay, so majority do not. And probably you will want to know how to get access to Shaheen and what other permissions you need. And there are some confusion. That's I think you were saying yesterday that there's some charging, or there's no charging. 𝐊𝐀 people, you guys don't pay anything. So I think even James had initially you think that, well, if I use it, there'll be thousands of dollars being directed from my payroll. No, nothing. So it's all for you. Even in Kingdom people can use it for free. All right. A little bit of story. Supercomputers. So we boast about being one of very few universities who have a consistent infrastructure for supercomputing. I have been to National Center of Supercomputing in Application in Urbana-Champaign. That's a US National Center. I work with Compute Canada. I know PRAISE European Center. I know Japanese and Korean research centers. Very few universities have this consistent supercomputing program. So in 2009, we had Shaheen I, which was a BGP computer. Okay, that was number 14th in the world back then. And how do we measure this ranking? So anybody, linear algebra, I think we all know. Linear equation, right? We solve linear equations. Dense linear algebra, right? So LUD decomposition, I think we did those things. So this is just a matrix solver. You run that matrix solver and see how fast a supercomputer runs it. And then you say, okay, this is the sustained petaflops. And then based on that, you rank this supercomputer. 14th fastest in 2009. Then we got upgraded in 2005 to Shaheen II, which is our existing supercomputer. It was 7th fastest supercomputer in the world. A lot of bragging rights, but it's not only bragging right, it's capability. It's capacity that these supercomputer offers. I know I have been to places, there is no university in the world that can offer this type of service to that small number of users. Sure, there are bigger computers than that, but these are national services, international services. So you should be really using these resources. And unfortunately, supercomputer, just like your laptops and iPhones, it only lasts how many years? When you update your computer?
5 years. 5 years.
That's the life of supercomputer also. So 5 to 7 years. Yeah, you see the pain. Yeah, it goes. But there are many reasons for that. You do not want to burn all that energy on the old technology, because the use of energy consumption becomes more expensive than what it is offering. So it's a very expensive program, but then the great stories that come out of it, that actually is the reward. And we have, as we speak, we are actually doing a Shaheen III negotiations also. So Shaheen III will be operational, hopefully, inshallah, 2023. So this is not just a bragging. I mean, you should all be proud of it. What I'm trying to say is that we have a consistent infrastructure, and we have consistent commitment from our senior management for HPC support. And this Shaheen III will go all the way to 2030. So we will merge into Saudi Vision 2030 if we do things right now. All right. So we offer, so we do not give you just a supercomputer, because there are some services like that. So cloud. So if you go to cloud, what do you get? You go to cloud and then you're alone. You have to do everything yourself. So where is the ticketing line? Where you say, well, can you please install Convert? Can you install Fluent for it? Oh, can you give me test case? So there's nothing over there. So we provide all those type of services once you get Shaheen account. So basic support, like installing your software, giving you test cases, and then you say, well, yeah, I can run your toy problem, but my problem is different. Can you please help me? So that is a consulting service. Now you're asking. So we provide consulting service. We have actually dedicated Fluid Code contractor who is going to work with you guys, and we will help you. Good morning. All right. So basically, I've shown you the statistics from you guys. All it is saying is that you guys think HPC is great. You guys think that Fluent is great, but you're not using it. So what is the problem? So based on so many years of feedback, I realized that there are still barriers. You still have barriers to go from here to there. So we want to reduce those barriers, right? So increase productivity. So you do not want to wait. I mean, at the expense of a little bit of ease, you are fine waiting 3 days on simple simulation and getting a result on Sunday, because it's fine. But we want you to get that result in 10 minutes. So I think our online audience are the majority of them, they are Saudi undergrad students. So they want to get some competitive edge. They want to join these programs. And then the hope is to train a new educated workforce for Saudi industry. So this was one of the big success story that happened in 2015. So it's an actual gravity separator vessel from Aramco, and it's a very complex flow. It's not a simple laminar flow. It's a multi-phase turbulent flow. The dimensions are huge. I think yesterday or day before yesterday, you went into a little bit of idea of this Reynolds number, because the dimension of the scale of your problem directly increase your Reynolds numbers. So these are of the order of meters, maybe 10, 15, 20 meters, probably even more. Do you have dimension? Oh, not yet.
No.
If I remember, they were talking about these vessels are of the order of, they are in soccer field. So they're really, really big. So when they're really big, Reynolds numbers are extremely high. So in order to do turbulent flow, yeah, can you estimate what was the mesh size for this problem? Million?
What, sorry?
Mesh size for this problem? Because I had said scales are big, Reynolds number is high.
Yeah.
Good estimate, increase it. 1.5 billion. So he is close. So 1.5 billion. So
I can see the
1.5
number.
billion, and then it was able to scale on the full Shaheen. So you'll learn what is scalability. So full Shaheen was running this problem, and the engineer is saying that, well, the week's worth of work is reducing to hours. So that's nice story. That's power of Shaheen and the HPC at full display. Having said that, this is not all we want. We do not want only these mega projects. We need to reach out to other people. So supercomputer can simply be used by people for doing simple MATLAB problems. You can use a supercomputer for a capacity machine. What does it mean? N per people, N per people, N per. You guys do huge number of parametric sweeps because you don't know any material property of your problem, right? You don't know your geometry. So you just do parametric sweep. You just want to run parametric sweep. You have 2D matrices. You want to populate your results, some output on these 2D matrices. You do that, right? So what you have to do, your single problem is small enough. You can get your result in one day, but you have to run 1,000 problems, maybe 10,000. If you are doing data science, many of your colleagues are doing data science on these artificially generated simulations. You do data science on that. In order to have any meaningful deep learning workflow, you need to have huge amount of data sets to train it, right? So all these parametric sweeps can happen on a supercomputer. All you have to do is write a simple Python script, have some intelligence in your input file where you can change the parameter with a script, and just submit this job. The whole workflow will be starting. So, and one of the real objective of our program is to increase the employability of students. So, I mean, especially the undergrad students in Saudi universities, when they get these certifications, I mean, they feel very proud about that, and they get connected with industry in these programs. They start talking to each other. So that's why I asked you guys to upload your bios so that people can see it. I cannot promise anything, but at least it's an opportunity for you to mingle and talk to other people. You can increase the scope of all these programs, but again, slowly. So here's the program that we are doing. So we have two streams. One is a simulation stream. One is a data science stream. I'm not going to go into artificial intelligence stream. Wait for that in September. We offer certification program. You are participating in that certification program. That's very popular, actually. We did not have this idea that certification program itself will become that popular. People really, really want to get a certification, and they really sit and go through every day, and with the hope that they will learn something. That's really, really nice. We are planning a sandwich course. What's the idea about sandwich course? I mean, you guys, sandwich, we know sandwich, but sandwich course, there's a gap. There is a gap between the students who are graduating at undergrad level or master's level and the needs of academia or industry. There's a gap. We try to bridge that gap. There are some universities, actually, they are offering these courses where they have actually partnered with industry. So that's our hope, that we can partner with Ansys and we can design these sandwich courses where you actually are ground ready when you graduate. And that applies more to undergrad students, actually, and master's students. PhD students have, I think, a different trajectory. So there are two services that we offer in consulting. There's a helpline. I'll tell you all the links and everything. So helpline is, well, I cannot find, don't call us if you cannot find your iPhone, but call us if you have CFD problem, right? So just call us and then there will be a ticket generated and then we will provide. This is a bit more than like install that software or Shaheen is too slow. I don't like Shaheen. I don't like, these type of complaints you can do somewhere else. But if these are problems where you say, okay, I learned cavity flow problem using laminar flow and turbulent flow. But my problem is multi-phase. I do not find that test case. Can you help us? Okay, we will get started with you guys. We'll probably give you a test case. But then you say, well, cavity flow is a very extremely simple geometry. Well, my problem is extremely difficult. Can you help us make the geometry? Or maybe I have a geometry. Can you help us make a good quality mesh? Or I have a mesh, but it's giving me negative Jacobians. Can you please help? So these type of things are a bit more in depth than just opening a ticket for installing software. Does this make sense? And then there is a helpline for project based. So I will give you a QR code. I mean, I'm particularly talking to my friends online. If you are in Saudi University or industry, just scan the QR code. It will take you to a form. Just fill that form. We will get started on that. So we provide project-based support. So if your problem is really complex and it requires some substantial amount of time, so my contractor will start working with you guys. So in a year, we can probably do 3-4 projects. But if there are more demands, we can increase that program. This is a glance of all the training workshops that we have been doing. And I mean, just say 1,000 of you have registered, around 600 people actually attended these workshops. It's a good number. And every year I see different faces. So it's not that the same person is coming out. So you're most welcome to come to every event. But since there is a repetition of program, because in a university, basic CFD is something we want to do every fall semester, because students are coming and they want to go through the basic CFD. And there's some structural mechanics program also that we offer. But then sometime we do turbulence, sometime do multi-phase. I think there is some demand for chemical kinetics this time, so we'll see. And sometime we do HFSS. So these are all different type of things that we do. But all of that depends on your feedback. If you provide your feedback right in detail, well, this is fine, but we want to do that. This also, we'll listen to you. This is a typical mix of the people who attend. So so you need to really understand. I mean, I'm talking to the people in class. I mean, you think that, well, it's just a cost event. It is a cost event, sure, but I'm targeting in-kingdom people also. So because that's one of the major driving force behind it, and that also gives you opportunity to know what is happening in kingdom, and they get a chance to meet you guys and what you guys are doing. These are some of the organizations from there where they are coming. No, that's again, I'm repeating these numbers. So just, I'll give you a minute. Just go through this thing. What do you understand from these 3 pie charts? It's a repetition, but well, I personally do not understand why it's happening. What it is saying is that you are Ansys user. You're not running on Shaheen, but you want to run on Shaheen. So what is that is missing? You want to run on Shaheen. So what needs to be done so that you become Shaheen user? So I think that, well, we need to do some hand holding and do some hands-on trainings. What I'm doing, I'm going to do after coffee, and then have a good coffee, because it will take, I mean, you have to do a lot of typing actually. I'll type everything. No copy and paste actually. Well, what you have to type things. Linux is typing. So but if you go through this thing, I think, in my opinion, you're more likely, because I think I understand your workstation is your favorite place. You're comfortable here, and so you don't want to go through this thing. But we'll keep on repeating these hands-on sessions, and with the hope that you'll get converted. Yes. Yeah.
When you say that, can you help industrial companies, or you help the post?
Well, I think I already answered when this question was posted. I think I already answered. So anyone from the room? Are we offering these services only to COUST? Oh, in fact, this is an exam question actually. No, no, we are actually offering these services to Saudi industry and in Kingdom, and there's a complete slide on that. I'll go very slow on that, so I'll come back to this point. Okay. Nice F1 car. I remember I told you that I need to motivate you guys. Okay, is this enough or not? So what do you see in this slide? Yeah, speak loud. It's okay. Okay, so let's get some terminologies out of the way. What is a speed up number? There's no mathematics, there's no deep computer science. What is speed up number?
It is the increment.
Yes. No, it's not. It's a ratio. Speed up number is that you take one core count. Normally it is based on one core performance, but you can start from anywhere. You run a simulation on any n number of core. Now you let's say double the number of core. Your time to solution should reduce. So the ratio of those times should be, the speed up number should be 2. That is the reciprocal of that. So you get 2 speed up number. So you should get, ideal is 2 speed up number. If you double your core count, your time to solution should 1/2, right? The speed up number should be 2, ideally. So what is happening? So on 1024 cores, that's a base. On 2048, we'll get 1.8. Ideally, it should be 2. Good enough. Fine, right? 4 times, we should get a 4. We are getting 3.4. Now, I'm sorry? Not proportional? I mean, so we'll come to that. That's a bit more in detail. But first, let me ask you, where is the difference going from 2 to 1.8? That's another exam question, I think. I'm sorry? So that's a good point. Again, the right terminology for that data transfer is communication. So now you have partitioned your problem. We will, in a parallel computing version, we will go through this thing. Now you is working on his problem, but he cannot independently complete this problem. When he gets to the point where he has to talk to this gentleman, you have to communicate. You say, well, give me your solution and I'll give you my solution. So that communication happens. So that is an overhead for parallel computing. So you need to hide this communication. You need to have a big enough problem so that this communication should be minimum. I'm telling you, at this core count, this is a very good performance actually. So at 4,000 cores, if you increase the problem size, and there are some hands-on sessions on that, you'll improve your parallel scale. This is called parallel scalability. So you will improve this thing. You were saying linear. Why you are saying it was not linear?
You saying it's not like use the discrepancy between the speed of an idea, right?
Give me an example. Are you looking at number 2 and 1.2?
Or I mean, you see it's a big
No, it's not delta. It's a ratio.
ratio.
The ratio is linear. So it should go linear, but it's not going linear because there's some loss that I exploit. So there's some communication, and there's something called Amdahl's law. I'm giving you this terminology with the hope that you guys do your work very well. But if you have to write a journal paper in something which is like computer methods in applied mechanics and engineering or computer and fluids, so you might throw some of these terminology that will make your paper look good. So Amdahl's law says that, well, your serial work, all codes have some serial work. And because of that serial work, you cannot scale perfectly. So unless your problem is embarrassingly parallel. I was giving you an example of the NPERC story. So if you do a parametric sweep, no communication needed. So you just change viscosity, viscosity, viscosity. Everybody is, all the processes are doing exactly the same problem without any communication. That will give you perfect scalability. But having said that, that's not the best use of supercomputer, because you're solving a trivial problem. The best use of supercomputer is that you solve one big problem, one massive problem, because you cannot solve this problem anywhere in the world. Parametric sweep is something that you can always do. Even on these workstation, you can do, you connect them, you can do this thing. But sure, that is also one use of HPC. Now, I'll show you some actual hands-on session. Seeing is believing. I mean, you'll run the same problem on one node. You run the same problem on 16 nodes. I did a screen save, so you can see 65 iteration, and it's almost 1,000 iterations. So it's real. It's not abstract. It's not number. It's not a theoretical thing. You'll see that, well, parallel scalability does affect your time to solution. Okay, this is a heavy slide. Let's go slowly. I think you covered pretty much all of these things in this workshop, in this session. So let's use this slide to repeat what we learned. So you learned about, I think I raised Ajay's, you learned about partial differential equations. I think, is it safe to assume any master student would have gone through partial differential equation? Or maybe there's some program where you probably don't go to partial differential equation. So, well, Navier-Stokes is partial differential equation. So you need to learn a little bit of partial differential equations. With every partial differential equation, you have some boundary conditions, norm and boundary condition, Dirichlet boundary condition, and then you have initial condition. It's a time unsteady PDE. Then you need to know that is your problem steady state or unsteady? I think Ajay covered this thing. I don't want to repeat it. So you would want, for the sake of computational efficiency, you would want it to be steady state, because that's faster. But if you are trying to capture some flutter, some maneuver, something which is really, really dynamic, you want to see the interaction of some shock waves, then you have to do unsteady simulations. Then you need to know a little bit of, are you solving implicitly or explicitly? What are the advantages of implicit method? What are the disadvantages of implicit method? Okay, what is the advantage of explicit method? It's cheap. You can just, at least one iteration, you can do it right, because you don't solve matrix. Explicit method, you just march in time. Navier-Stokes explicit methods, you don't work. Implicit method, you have matrix. You have big matrix to solve in each Newton iteration. Laminar, turbulent, multiphase. I think you went through this thing. We also cover structural mechanics problems in trusses, start with trusses, bars. So we do that type of thing. And then I think coupled field problem. So coupled field problem, again, there are two partial differential equations, and then you have interface problem. So you solve these three together, and that's your coupled field, at least two multiphase. Okay, so again, I think you cover modeling, meshing, and problem setup, and then you take it on a supercomputer and do. I think we will do all of that with hand, and I think we have been doing it with the students, and they take a good interest in all of that. Some structural mechanics problem we covered, big problem. Some electromagnetics we did, basic CFD. I think this problem you probably did. Some airfoil, external aerodynamics, vortex shedding, very, very classical. I think the cavity flow problem is a classical steady state benchmark, and vortex shedding is a classical unsteady benchmark. If you have done any CFD course or any CFD research, you must do this thing. Otherwise, yeah. Backward facing steps, multi-phase flow. It's a flushed tangle. It's a very cool problem. So, and then we do some HPC, and this is a glimpse of one of the training that you're going to do. So you'll go line by line, and then you'll do all of this session. And if you do everything right and all the stars are aligned, you will get this picture. very few of you actually get this lecture done. I don't know. I mean, this is just a typing actually. There's 26 commands. So if you just type correctly, it will happen. But again, there's another effort actually we are doing that, well, we want to make these GUI type of things, because probably you guys will find it more easy to press buttons rather than type. So that's us going out of the way too. Okay, so we do get feedback from all of you, and that's really important. So this is just a glimpse of some feedback that we got from the first attendees, and then a little later. And then we do, that's a compilation of their suggestions. We try to accommodate, and then after 9 attempts, we are able to accommodate pretty much everything. These were the things that they were saying. Only thing that we are not able to do it, maybe you can take this message back home, that they want some laptops and iPads also as a prize money. So this is something that maybe pens, something you can bring next time. So as a token, so we can ask a quick pop quiz. That's one way of increasing the interest in the room. Yeah. So we just do a pop quiz, and then if somebody answers. Right now I have nothing to give, so I cannot ask a quick pop quiz, unfortunately. Okay, so we upload all the material. So you can go to our websites and you can get the old material also. So I think some of you already asked that. Well, I'm interested in that event. You'll go there. Stream 2, I'm not going to discuss. I'll discuss it in September. Artificial intelligence stream. It's very, very hard actually. In certification program, actually, we changed the themes of certification program. This time we are getting certified on basic CFD. Around 250 people already got certified on that. Some pictures. Okay, so that's the future plan that where I am right now. So after this session, I'm gonna do a half-day session, something like that, routinely with you guys, based on your feedback, which is basically just a hands-on session. Just hands-on session. We'll just sit, have coffee, and then we'll just go through it. It will be more interactive. Even the later part of today will be more interactive. Then I plan to do a 1-week summer school, so in which you will have chance to do different type of trainings over there. And then I want to merge the data science into that summer school also, and a sandwich course that we do. That's where we are heading in the next 2-3 years. So then we started consulting services, because the motivation behind the consulting service was that, well, we are doing all of this thing that I said before this thing, but the uptake on Shaheen usage for CFD people is not happening. So then we realized that, well, some of you need a bit more hand-holding. So we started consulting services. What it means is that we actually have all these things available. You have the computational resource, we'll install everything, we'll give you test case, all of this thing happening. But the missing thing is that, well, human consulting was missing. So we subcontracted a consultant, and then we are providing this consulting service. Another exam question, I think. So the beneficiary of this consulting service is Saudi universities and faculty. So this is answering that question. So they can use that, they can just swap that, scan that QR code, and they can do it right now. Saudi universities and they can benefit, and Saudi industry can also benefit from that. I mean, you might ask that why this consulting service is based on Ansys. Why it is not based on other code. It's just numbers. Numbers, I mean, most of the people are actually using Fluent for CFD. So that's an easy choice for that. We set up a mechanism for processing and approving these projects. And then on the helpline side, we just take these tickets. You just ask these questions, and then we respond. Some of them, they are very, very simple. tickets like, okay, do this thing. Okay, here it is. I can convert this file to this format. Okay, it's done. But some of them, they become projects. So they take more time. And on the project side, we are currently supporting these 3 projects. You can see that one of the project is from Aramco. One is from university. The third one is from Baker Hughes. So you can see some of the topics that we're working with them. All right. So here's the answer to that. So you can use anyone in the room can scan this QR code and a form will come up, and then you can just fill up. It's just 1-page form. And then any Saudi friend who is online, scan this thing and a form will appear, fill it up, and then we'll get started. And any of your questions, just use this helpline. Just shoot an email here and we'll get started. All right. Just a recap. 2 training streams: simulation, data science, education, certification program, sandwich program on the way, consulting, helpline, project-based support. Right. All right, thank you. And I'll give you a few minutes to, if you have any questions. And now I think online there will be a lot of questions. So if there are questions, I'll happy to answer them right now, because this was actually for online audience.
Yeah.
Because they need to use these services. 𝐀𝐿 people actually know much about these things already. Okay. So this is for you guys, 𝐀𝐿 people. How many of you know how to access Shaheen? You don't know. Do you want to know, or we can skip this?
What's the difference between, because I use 𝐸𝐵𝐵𝑒x.
I'm going.
I'm using 𝐸𝐵𝐵𝑒x. So is it any difference?
Okay.
𝐸𝐵𝐵𝑒x,
Mhm.
yeah, whatever. So is it any
𝐸𝐵𝐵𝑒x is a goat in Arabic.
okay.
Yeah.
So,
Shaheen is a bird.
okay.
Yeah. So
So is there any difference assessing?
between a bird and goat.
Yeah.
So think about it. What is the difference between bird and goat? So that's there's a reason I'm telling you. The birds fly,
Yeah.
right? Shaheen flies. 𝐸𝐵𝐵𝑒x is very resilient. Goats. This goat is actually like any Arabic speaking person. What is 𝐸𝐵𝐵𝑒x? No. No. Yeah, Arabic.
I think it's animal.
So let me try to explain and tell me if I'm wrong. Then I'll have to change my sales pitch.
Is the name again?
𝐸𝐵𝐵𝐵𝑒x. 𝐸𝐵𝐵𝐵𝑒x.
𝐸𝐵𝐵𝐵𝑒x?
Yeah. So it's what we were told. That's why we named. It's a goat that lives in the mountains.
وعلى الجبل yeah.
So it's very resilient thing. That's how we named our smaller cluster 𝐸𝐵𝐵𝑒x. So that answers your question. So 𝐸𝐵𝐵𝑒x is a mix of many things. It's not an HPC thing, but you have all types. You have GPUs, you have Cascade Lake, you have Rome, you have AMD technology, you have Intel, you have pretty much everything. And you use different type of workflow, but not at scale.
عليكم السلام ورحمة الله.
So don't expect it to run on 1,000 nodes or 5,000. So it's more like a small 1 node jobs, but many of them are, but you can get benefit of large memory node, for example. So it's a mix of everything. Okay. And Shaheen is a very uniform machine. So HPC is a uniform operation where you scale problem. So yeah. So, but again, does this answer? So I'll come back to the question. So you guys want to know how to get access to Shaheen, right? I hope so, right? Okay, accessing 𝐀𝐍𝐒 services. So what do you need to know right today? If you have nothing, what do you need to start getting on running on Shaheen? You need computational resource. So this again, this is a terminology. It's after coffee, there's a lot of hands-on sessions. So right now I understand it's me just talking. I'm trying to make it interactive, but that's just the information going your way. And there are some exam questions on that. So computational resource, how you measure computational resource in the terms of core hours. So that's for you also. So once you have a supercomputer, so these are the things that you will be thinking, accounting. So I'm basically talking about accounting for a supercomputer. It's a resource. You want it to be accounted, right? So there are 1,000 users. So you give some core hours to them, and then you hold them. Once they exceed that core hour, you say, well, alas, you cannot use beyond. So there's accounting. So you basically ask for core hours. That's the first thing that you need to know. Computational. What is 1 core hour? 1 core running for 1 hour. That's a resource, right? So typically, a basic proof of concept project requires 2 million core hours. So where you say, I attended Drew's training session. It's very nice. I have a problem, but I want to just get started on Shaheen, and I want to run 𝐀𝐍𝐒. I want to do some strong scalability to see, and then I want to add some turbulence and want to do some turbulence studies. That's a project proposal that I just spelled it out. So you write something like that, you get started with 2 million core hours. 2 million core hours is something that is a development allocation, right? Once you do your proof of concept, now you're press of a button ready for massive simulation. Then you write a production proposal, which is a bit more demanding. That because now you're gonna say your question. Now you're gonna say, if you give me these 20 million core hours or 10 million core hours, that's a scientific contribution that I'm gonna make. So you need to convince the review committee that, well, give me resource, because people are competing for the resource, right? So it's some paperwork for getting the computational resource. By the way, the consulting service that I said, it does not require any paperwork. That I have done everything for you guys. That's a startup program that I'm doing. But for general usage of Shaheen, that's what you have to go through.
2 million per hour, there will be review or not?
I'm sorry?
2 million per hour, there will be review or you will be
I don't, I mean, it's not me, it's a review committee do that. For CAST people, for CAST PIs, it's a faster process for development allocation. This is called development. Let's get some terminologies done so that it will make it easy for you guys when you're going to talk to your professors. You will go to a professor and say, well, oh, I heard something and we need to write something. You know what will happen? The professor is going to ask, okay, very good idea. You write it. So you're going to end up writing these things. So I'm telling you guys. So these terminologies, because you are going to come back to me. So development. So you're talking about development allocation that get processed pretty fast. But for external people, even development allocation requires some more paperwork because there is more different type of overview for that. So you need computational resource. So by the way, 2 million core hours. How fast? How much is it? So think about it. I mean, you learned something, some simulations. Yeah. So how many simulations you will be able to do? Rough idea. You don't have to calculate. So if I give you 2 million core hours, what you're going to do? So you'll take your problem, whatever you have, you're running on your workstation, you'll run it over there. Workstation is one node. So you know that nothing is big. So you run the same thing over there, and then you'll increase the core count over there and see if it scales or not. So 1,000 cores using 1 hour is 1,000 core hour. And 1,000 core working on one problem for 1 hour, you get sizable amount of science done. If it is steady state problem, unsteady state problem can consume pretty much of it. Just giving you an idea that CFD is extremely resource hungry operation. So if you have a detached eddy simulation problem and you have actually nailed down all the parameters, and that happens a lot also in CFD, you think that you are ready. you run something, it's going to block. The time step was not small enough. Anything can go wrong. Mesh was not right or whatever. So when it uses a lot of resource, so you need a lot of judgment to make run these simulations. Then you need Ansys license. Now that's also probably an exam question. All of you by default have license. So we procured license for entire entire 𝐀𝐒𝐒 community. Students, researchers, everybody can use it. We extended that license and all in-kingdom users can use our licenses, provided that there are two caveats on that. The caveat number one, university can only use our license, Saudi University, let's say KFUPM, KAU. They can only use our license if they have their own at least one license. Wasim, this is information for you also if you don't know. So, I mean, if they ask, can we use that? So if KFUPM has one license, they can use our license. That's one caveat. For industry, they can only do Aramco, SABIC. I don't know, you guys fall into industry or we have no, but you fall in industry or national organization or you're not university. Yeah, but okay. So for industry, I'll think that I'll say your industry. You can do all the work which is open research. I think we had a discussion on that during the lunch, but I'm using that discussion to tell our other. So open, what do we mean by open research? Open to everyone? Yeah, everyone can access and no confidential, no IP related work in there. And on top of that, all this operation, including the Shaheen operation, you can do certain type of research, so, which is outside the US export control regulation, because this operation runs under US export control regulation. All right. Then you need support and then you need consulting. So you have all these things, you can get started on Shaheen. I think I explained you a lot of things about that. A development allocation could be very simple actually. But a production proposal would require something like I think it's safe to assume that you must have written journal paper. So in journal paper, in the introduction part, you start defining your problem. That's my problem, and that's what other people have done. And that is how my problem is different from them. So you have to convince this to a reviewer, otherwise your journal paper doesn't go through, right? So you have to say that this is new, or this is something fundamental. So that is something that you're going to write in this project proposal. Then you break down your project into n number of simulations. That's a difficult thing. You do not know, right? That if in order to develop this catalysis machine, or in order to do this numerical wind tunnel, how many simulations you need? But brother, you do your best so that you justify the resource, because you need to, at the end of the day, you're going to say, I need 40 million core hours. So we are going to see how you come up with this 40 million core hours. How did you break down your resource? That's something that is done in any research grant application also. Describe your typical simulation. So now you're going to describe your typical solution. In a typical solution simulation, how you're going to run. This will be my typical problem size, mesh size. This will be my typical duration of simulation, because there's a catch. Simulation on Shaheen can only run up to 24 hours. You can submit your job only for 24 hours. If your simulation need more than 24 hours, what do you need to do? I'm saying, no, not to fill a form. No. We are not that. So that will be fun, right? I mean, your simulation running and it is going more than 24 hours. You have to fill the form and here's the form. So you restart. So you have to fill a form if you run out of your entire allocation. Then you have to fill in. This was just joke, because we need joke. We need coffee and we need joke right now. So if you cannot finish your simulation within 24 hours, what you have to do is that you need to have a restart. I mean, in CFD, that's a standard thing, but in other domains, but some codes might not have a good restart mechanism. Actually, I'm telling you, some of the codes, your competitors do not have good restart mechanism because of many reasons. So that's why you need to know your typical simulation very well. Then, of course, once you do this thing, you know your computational cost. Now you know, okay, I need 23 million core hours, and then oh yeah, they know. There you go. It's a good resource justification, right? Then you need to list all the codes that you're going to use. Not only simulation, also post-processing, pre-processing. So what you're going to say, while I'm doing this cavity flow, for some reason, nobody else in the world has done this thing on this random number. I'm just making it up, obviously. And I'm going to run that many simulation. I need this many resource. I'm going to use Fluent. This is the code, and we have access to Fluent because we have cloud, and we are going to use CFD post or ParaView for post processing. That will be the whole story. Any questions on that? And any doubts? Because you will be doing all this paperwork actually.
What if I want to make a publication of not like by myself, as from my university or something? I just like contacted the professor around the world and I want to make a publication and I want to use your supercomputer.
Okay.
I'm not sponsored by.
Okay. Let me start answering, and then in the process, you will get your answer. The first thing, I think, the more important thing is that if you're a professor, let me talk about KAUST people first, and then I'll come back to you. So let's say, anyone, who's your professor? Who's your professor?
Bill Roberts.
Bill Roberts. Let's say Bill Roberts wants to work with San Diego National Lab. That's it. I know he's not. It's an example, and he wants to add his researcher onto your project, right? He can do that. So you can, any collaborator of KAUST faculty member can become a Shaheen user. That's not a problem. Now, your problem is different. You're not KAUST. Okay. So first of all, you need to follow the steps to become a principal investigator from your organization. So you become a PI for this project. Once you become PI, you can have any collaboration. That's not a problem. Then you are the owner of this resource. Is it clear?
Yeah.
So you can collaborate at the time of project also. You can say that we are collaborating on this project, and that it has some application. It is groundbreaking research, and we want this resource. So it can. Does this answer?
Yes.
Anything else? Yes. No.
We have a proposal passed by Shaheen, but this is the code in 40IP. Can I directly use the answers by that proposal, or I need to write a new one?
So you are VASP user?
No, my colleague, he has the proposal passed, and then my supervisor suggests to add my name during the extension.
Yeah. So you're a material science person.
Yeah, chemical engineer.
Chemical. So you're going to do CFD also?
Yeah, and also can we combine that proposal with two or just?
In principle, no, because that's why you see in here there are list of codes. So in this proposal, when who's your professor? Okay. So when he wrote the proposal, he listed the codes. You see the bullet point here? So he listed the code. He must have written over there VASP, GROMACS, Quantum Espresso, right? So these are the codes that proposal was reviewed with that mindset, right? So in principle, you need to write another proposal. That's okay. That you can have another. So that will not be taken against you. So you did something and maybe the idea didn't work out. You write another proposal. That's not a problem. So I suggest write a new proposal, and if your professor is writing, okay, let him write. That's fine. If you have to write, and you need help, you just come. So this is part of my job. I'll help you guys. So I'll give you some guidance how to write things. Okay.
Thank you very much.
And if you just want to do simple cavity flow, maybe during the hands-on session, you will do it right now, actually. So if it is just like a one day you want to do it, you'll do it right now. So, but if you want to do it for research, write a proposal. Okay. So project proposal is clean. Now, I'm sorry, this is paperwork, but if you don't do it right, it will drag, it will take time, and then users run away. They don't come back. So, and I'm offering you, don't let me go. If you need help, just work with me. We can write together. So Geo can verify that. So we can work because it is in our interest. I know a little bit of CFD, so I'll work with you guys. Don't worry about that. So once you have the project proposal, now you have determined a principal investigator. PI is determined, which is basically your professor, right? Then he can add any number of students on that. So each of that student needs to write a simple form, which is IAA form. So let me take a 1 minute break. How was the session?
Very good.
You like it? Okay, good. They're coming back from after teaching 9th graders. Okay. Then this is important for you. It doesn't apply for 𝐀𝐒. 𝐀𝐀 is 𝐀𝐀, so we don't need to verify the organization, right? But if some other university comes, international university, or from Saudi university, or Aramco, we say, okay, fine, we are going to serve you, but your management needs to sign this document. This is called organizational access form, right? What you're signing over there, you're signing over there that we're not going to do certain type of defense projects, certain type of things. So because that is compliant, we have to be compliant with whatever is happening on Shaheen. So that applies to some of your research. So basically, statement, no weapons related work is being done, and some senior member from your organization will just sign it. And when he signs it, he appoints one person, one researcher as the reference person who will from there on, because his time he doesn't sign every day. So you get his sign, and then you will name yourself or two people that you will start signing on the behalf of organization from there on. Does this make sense? Is this process clear? Okay, and there's a link. So from here, you can go to these account application, all these forms, then you can find out. And I'm telling you that you will find it a bit difficult to do it. So the moment you do that, set up a 15-minute, 30-minute Zoom meeting with me, download it, try to do whatever you can, and then we'll get started. And it will be done within a day. All right?
I think there is a similar question for this.
Yes.
Uber is asking if you could share some samples of filled forms for the guidance. I hope this is answered because you are going to help them.
So the thing is that I'm happy to share some project proposal. I mean, IEAs and OAs are straightforward. It's just you put in their name and that's it. Project proposal, the thing is that, well, unless Geo agrees to give his consent that he can share, I cannot share someone else's research with anyone. So that's a thing. But the better thing is that, well, just set up a Zoom meeting with me and I'll work with you. All right. This is actually an exam question. So this is Wasim answering that gentleman's answer. All Saudi academic institutes with Ansys license can use 𝐀𝐒 license. And there was another question, discussion yesterday. Was it you? Somebody was saying that, well, we have to pay for every course. So 𝐀𝐒, the Fluent actually has a core-based licensing. So when we get Fluent license, we cannot use it on full Shaheen. So we have to pay for, okay, we can use of, I think you guys have 256 core license, 256 core license. If your problem is, I can scale on 512 cores, you cannot run it, right? So you have to wait twice the time on 256 core and just, so that's the charging model of Fluent. So we have 11,000 core license. And I'm going to show you at around 12 o'clock, even that is not enough. I'm going to show you a simple cavity problem. If you want to go higher in Reynolds number, even 11,000 core, you can still keep scaling, but I ran out of problems. So, and that I ran out of the license at around, yeah, I'll show you the scalability study. Okay. All Saudi industry partners can use Ansys for open research. So I think that applies specifically to you. So, I mean, I'm using 1% example because because he's asking question. If you're asking question, I'll make your example. So but that's very tricky part. So, and you have to design your proposal that that's an academic process, academic exercise, and we are going to publish this result. Then you can use Shaheen, then you can use Ansys for that, right? No IP related, no secret work. So these two things are available. Then your job is not done. You still have to do your job. Your job is to come up with a good problem that can benefit from this scalability, meaning that the problem is big enough and it has good justification, because you do not, if you can get if the solution is linear, one element is enough to capture the solution, right? You can kill yourself and put a 1 million node mesh on a linear problem, you still get a linear solution, but you don't want to do that just to show that the Shaheen is scaling. You don't want to do that. So it's like, mathematically speaking, the solution space has to be sufficiently refined that your numerical solution will never be able to capture this thing. And then, so for example, if the solution space is quadratic and you're trying to capture it with piecewise linear shape functions, you will never be able to capture this solution, because that's what Ajay was showing, that all the way to 10 to the minus 17, linear elements will never be able to get exactly quadratic, because it will always stay piecewise linear, right? So what is the message? Take benefit of this opportunity, come up with an extremely good example and make a big success story, just like a GSV story. So that's more relevant for our Saudi partners. So come up with a really nice project for your organization. If you make a big splash, then the follow-up will be great, because then a lot of things will happen. But for CAUST students and research, you guys are doing steady problems. So I mean, you have a smooth operation. So you really don't have to go through out of the way to make a success story. You just to carry on with your work. Okay, first step is obviously, as I was saying, that just shoot an email here and I'll start working with you guys on paperwork. I still have not told you, proven that, well, what is the real benefit of Shaheen. I'll just take 2, 3, 4 minutes and then we'll take a break for coffee. Okay, some detailed concepts are going to come in the parallel processing lecture, even not that much detail, but these are the things that you need to know. Even if you're not a computer science person, even if you're not coding, you need to know this thing. There is something called profile of a code. What is a profile of a code? You need to understand how the code is performing. So you start with reading the input file. Can you speed it up by putting it on 1000 nodes? Maybe, but most likely not. So this part is a sequential. So you need to understand the profile of the code, which part of the code can really benefit from scalability, from parallel processing. Normally speaking, which is the most time-consuming part of the code? Where CFT code spends most of its time? Meshing, but you only do meshing once. When you're running for a month, let's say. So most of the time consumed is not in meshing. Human time, yes, but computational time, I'm guessing. Where the code, so what is CFT code is doing? It's reading a solution. reading the input file, right? Then what's it gonna do? It's gonna do domain composition. Matters. Anybody heard matters, far matters? No. Graph partitioning. So you need to distribute the matter. Still not a big problem. You start your Newton-Raphson iterations or time step iteration. Still not a problem, just a loop. Where is the real work? Matrix, linear solve. So you do at the end of the day, you solve AX is equal to B. Doesn't matter, you are unsteady, steady, linear, non-linear, elasticity, plasticity, Newtonian fluid, non-Newtonian fluid, Maxwell, whatever. If your method is, if you're doing implicit method, you are solving AX is equal to B. That is where you are spending most of the time. And that is where you need to use distributed computing. And these, when you are calling these libraries, so Ajay was saying that he ended up writing his own code. So you probably ended up writing your own linear solver also. So now these days, the trend is that nobody writes linear solver. Sure, if your professor is saying that, well, it's a testing exam, do that. For real world, nobody solves linear solver. You use PETC. You use state-of-the-art available linear solvers. So you need to know a little bit of your profile of the code, because once you know profile of the code, you will understand that will you benefit from shared memory or distributed memory? If your code is serial, that's another exam question. Probably not, but I'm just saying it. If your code is serial and you run it on 1000 nodes, how much speed up you expect? I'm sorry?
1x time.
1x time is mean that equally slow, right? No speed up. You will not get anything because your code is serial. So that's what goes into understanding the profile of your code. That's an extreme example that, well, I think nobody would want to run a serial code on a parallel cluster, but that's just to understand, so that you understand. Parallel speed up, I explained you guys. So now you know this. You have your problem, you don't change anything. You have your problem, you double the number of resource on it, core count, you reduce time to solution, take the ratio, that's your parallel speed up. So ideally, you should get parallel speed up of 2 if you're doubling, but probably you will not get it 2. If you get some, is it possible that sometime you double your core count and your time to solution is even worse than the before? Is it possible? No? We can see. Yesterday, Ajay used what was there was CFD. What's the acronym of CFD? Somebody said colorful something.
Yes.
Colorful fluid dynamics. Colorful fluid dynamics.
Colorful fluid dynamics. Back in my time, I mean, people used to say, well, you guys just make nice pictures. I mean, it has no. So, no, you cannot get. What was the question actually you were addressing?
Slower distribution.
So core count. So why you think I try to explain Amdahl's law a little bit. So why do you think? Okay, let me tell you. Yes, it can slow down. So why you think it can slow down? And this is really important because if you do not understand, and if you are overkilling, you just without doing any investigation, you take your classroom mesh and put it on 32,000 cores of Shaheen, and you say, oh, it takes 3 days to finish. I mean, on my computer, on my workstation, it takes 5 minutes. It's possible. And I'm telling you, it's possible. Why it is possible? Yes. So communication varies at least linearly with the number of partitions, domain partition. That cost is always increasing. Now, the distributed computing is a diminishing return. So you get a lot of return if you use from 1 node to 2 node, well, you will probably get 1/2. But if you keep on dividing your problem, at some point, your problem is so small, well, it doesn't matter. It's a diminishing return, but the communication cost is already going. So you can see this trade-off. So at some point, you will actually be slower. So we will go through this thing. So you start plotting this thing, and this thing happens with increasing core count. All right. I think we covered domain decomposition. So seeing is believing. Let's stop talking. Look at it. Yours. I'm not going to say anything. What do you see? The picture above, which is probably one of the online people, they say, well, your screen is frozen. No, it's not frozen. It's just running on one node. And what's the picture below is doing? 16 nodes. So you can see the guy is stuck at 10 iterations, and now we are down to 140 iterations. You really seeing is believing, because you have to do it and see it yourself. Otherwise, these are just talks and the theoretical numbers. You have to run it and see. You really do not want to run it on one node. Why would you want to do that? You have resources. You run it faster. Okay, let's keep moving. In fact, my screen is frozen. I was making a joke, and it is actually got frozen. Okay. So what do I do? Restart or coffee break? Oh, it's just crashed. So I think practical jokes are not allowed then from now on. I think we are almost done from this thing, and then we'll. Yeah, that's actually the next was the last slide. This is again for your papers. So if you do whatever you are doing in your research, and you want to show scalability. So there are three ways of showing it. And one way is the real professional way of doing it. But let's see. The first graph on the left is just showing that as you increase the number of core count, your time to solution is decreasing. It doesn't look very nice, actually. It's so when you plot the same thing on a log scale, now you see a linear performance. So that's how you write report your results in a paper. Okay.
I think that does also have the answer to the earlier question, why we have discrepancy between the linear and then this when we increase the number of cores, because it looks like this is a log function between the time and the core count. That's why it deviates from the linear increase.
No, that's fine, but even in the log scale, it will start deviating. So
it's even, okay.
Even. So right now it's a perfect scaling right now. So if you keep on increasing, you will see that plateau. And the table below is a speed up number, which to me makes more sense actually. It is more easy to understand. But on the papers, you report log scale. Now, I think we are doing pretty well with time. So let's take 15 minutes break. And do you want to ask questions right now, or okay? If there are any questions, let me know. Yes.
Other domains, with the dynamics.
Yes.
What's the most common topics that using playing figure?
Oh, that's a very good question. I think our biggest users in the terms of resources is CFD, because you know that CFD, if you guys want to get coffee, please go ahead and you can hear me. So CFD is the most resource utilization operation, but number of users are material science. So KAUST has a huge amount of material science people.
Dynamics, right?
Molecular dynamics or quantum mechanics. So DFT people, I mean, she is from that group. So DFT is huge. Before we get to the handout session, let's go a bit faster, because I covered a lot of things already. So I will just rely on you guys, one of you guys, telling me something and then I'll go faster. If you don't tell me anything, I'll be stuck on these concepts. So a little bit of basics on parallel computing. You like fishing, right? So if you go fishing alone, how many fish do you expect in an hour? You got a 2, 1, 0, 0. Oh, yeah, yeah. I understand. I understand. So 2, this guy, how many he has? Oh, he has 0 actually. So more the merrier, right? More fishers, more fish. Not difficult, right? Put more people to work. You'll get more work done. What is the catch? The catch is the work needs to be done at the same time. Separately is fine, but there are 2 different paradigms for doing together or separate. We'll go through it, but important is at the same time. Otherwise, there's no benefit, because I can wait 2 months to get those. One guy can do everyday work. I want all the work done on the same time. So simultaneously, so that is the concept of synchronization. So it's a terminology that you concurrency, synchronization. That's important, right? That's parallelism. Do a lot of the work done, multiple work done at the same time. Okay. There are different ways of exploiting parallelism. The different parts could be different tasks or the same task on different piece of the problem. Now, what does it mean? Anybody want to take on that? So task-based parallelism or data-based parallelism. Task-based parallelism is something that your code is doing this step, this step, this step, this step, right? So if you can assign different work to different processors, you get work done. That's task-based parallelism. You give different tasks to different processors. That's task-based parallelism. That is the basis of multi-threading. That is the basis of OpenMP. That is the basis of shared memory parallelism. So these are terminologies. You must be thinking that you didn't sign up for this parallel processing course, right? But trust me, it's going to benefit you. What is other thing? You can also exploit parallelism if you do same work, exactly same work, but on different pieces of puzzle. You can exploit. So there's a big work. All of you are searching that you like Black Queen, Queen of Spade. That's a task. You're all searching. You're doing same work, right? But on different piece of data, different piece of problem. So these are 2 fundamentally different way of doing parallelism, right? Now we are formally defining this thing. Shared memory parallelism, distributed memory parallelism. And then you can combine this thing. It's a hybrid parallelism. Let's not go into hybrid. What is shared memory parallelism? Think about it, and the answer is coming. But think about it. What is shared memory parallelism? What do you think? Say anything.
The same capacity and distributed to many users.
No. Shared memory parallelism. Yes, go ahead.
When one computational unit uses another computational unit capacity to do the task somebody did.
Let's extend it. Shared memory parallelism means that multiple people, multiple processes are doing the work, but they are accessing the same address space. Now that's computer language programming, but they are accessing the same data. So the data is same. There's a pool of data and you all have access to this data. So you are accessing this data and you are doing either different work or same work. But you have access to the entire data. What is the problem? What is the limitation of this model? On Shaheen, you will only be able to use one node with this code. You cannot do multi-node parallelism. So you can get whatever benefit within a node you can, but you will not go beyond this thing. What do you have to do to benefit from 2 or more nodes? Number 2, distributed memory parallel process, parallelism. So what is distributed memory parallelism? Now, all of you will be doing same work, but there's a priority task that we have to do before we start doing this work. What is that work? What do I have to do with data to do distributed memory computing? I have to go, you can speak.
Breakdown, have to break down into simple.
Absolutely. Breakdowns, decompose, partition, load balance, all these things are going to come in now. So if our task is to find the maximum number. Okay, what is a good example? So I have a list of students, a billion list of students, and they have grades. So I want to find out who scored maximum. So what are the different ways of doing it? I say, okay, don't worry, you guys enjoy your vacation. You're already tired. You're already cursing me. I'll do all the work. You guys go on vacation. I'll do my, and then you come back on vacation and I'm still doing it. So that's not good. So what are other ways of doing it? I say, okay, all of you guys work with me and start looking the whole data you can access. I'm giving you the Google access to this whole data. You guys all can access this thing and then let's search out. So hopefully we'll get it done faster, right? Yes. But not optimally, because you do not know where she is looking, which data. So we have not set rules that you will only work on this thing, you will only work on this thing. So better way of doing it would be, I say, okay, let me do first some work and then we will exploit the benefit of your brain. Let me do domain decomposition, partitioning of data. So I'll look at all of you, you are 30, I'll divide a billion with 30 and I'll give you whatever, what did I do right now? This was also partitioning. So I give you different tasks. Now, do you need any communication with you if you're doing this work? No, you'll just look at your task, and you just report to master. Oh, no, don't call, not master. Rank 0, I'm rank 0. You just tell me, you think he's the highest rank. Everybody is going to tell me this thing. I'll just run a maxima command and I'll find the answer. That's a better way of doing it. I think now that I've spoken a lot, we can skip a lot of slides now, because now it is clear to you. On a single dimensional array, domain decomposition, data decomposition is straightforward, right? It's simple. There's no rocket science. Same idea is for 3D domain decomposition. Let me take a bigger jump and then we can go faster in this lecture. So what is 3D domain decomposition? So you have 3D mesh, right? Don't think of the linear solver. Don't think of what this guy will be talking to. Don't worry. You just treat a mesh as a graph problem. Do you know what is a graph problem? Every computational node or cell is connected to others. So you make a graph. All CFD code, they make graph. And it's called element connected. You do that. And then there are codes, matters, power matters. You just send them this graph and say, divide it equally on n number of partitions, which is my process. And they do that. How they do that is important. I think some of the slides are going to come. Do you see that in the example that I gave you, it didn't matter that if I do random distribution or I do some smartness in dividing, and this was totally a random problem. So there was no advantage of me doing partitioning in a better way. But in computational partitioning, you'll see if I do a smart partitioning, I will reduce my communication time. Is the question well posed? You understand this question? You'll get the answer later. Good.
So the difference between the shared memory and the distributed memory is that the shared memory are linear linked together in that the solution of one would affect the other, but the second is not? Is that what it is?
The fundamental thing is that in shared memory machine, you do not do data decomposition.
Okay.
You think of it as the whole, all processors have access to the same data. So you do not have to rename local arrays if you're a programmer.
Okay.
So you have access to the entire data. There are advantages, there are disadvantages, they are coming. So I'll skip this thing. Okay, let's take a puzzle example. So you have a 1,000-piece puzzle. You want to do it. No problem. If you are a puzzle person, you'll do it. Let's say you do it in 1 hour. If you're really good, I cannot do it in 1 hour. But let's say. But then some guy named Tim comes and wants to play with you. So how you want to do it together? You start from your side, I start from my side. Now, can you do it in 30 minutes? No, I don't think so. If the world is ideal, yes. Because one person was able to do it in 30 minutes or in 1 hour. 2 people will never be able to do it in 30 minutes. Why? Why? At some point, there are 2 things coming. So you will, let's play. Your turn. This is your piece of puzzle. Try to grab it. I'm grabbing it. So what do we do? We are contending for the same resource. We are fighting for the same resource. So when you fight for the same, because we have not done clean partitioning, we have not assigned. No, you cannot touch this. No, you cannot touch this now. This is my domain. So we have not done this. There is a contention. Contention is a loss of a resource. And then what else is there? At the interface, because these puzzles are not totally independent tasks, right? At some point, I need to say, oh, I cannot fit in here. Does it fit with you? And I start talking to you. Talking is good. I like talking. But in computer programming, more talking means more delay. You don't want to talk more. So there's 2 overheads in this paradigm, right? So you do understand we will never be able to get it done in 30 minutes. Now, more the merrier? Maybe, yeah, but there is a bit more overhead. You'll get things done faster, but not optimally, because now as you're increasing these people, contention is increasing and communication is increasing. At some point, you'll get diminishing return. Is this idea clear? You don't have to go into the detail, but do you understand? So what is the message for you? Do not run your small problem, 10 by 10 by 10 cavity problem on 2,000 cores. Don't do that. These 2,000 cores will be sitting, just competing with each other, fighting with each other, and not having enough work to do.
Distributed parallels, that's better for that.
Yeah. Let's see. So now we are going to distributed. So now what do we have to do to solve this puzzle?
Each will define his domain. Okay.
So we did. So there's some pre-processing. So 1,500, 500. You play your stuff. You play your stuff. Can you complete this task if you do not have mobile phone to talk to each other? No, you cannot. You cannot. Some of your puzzles will be island. You need to match the interface with him. So some part you'll be able to do it independently. Some part you say, hey, tell me, does it fit you or no? So that's, even in distributed computing, you have a problem of communication. Now, I think you can understand if you do that distribution smartly, you can minimize communication.
Yeah.
If you totally randomly just throw the piece of puzzles, then it's a maximum communication. On every piece of puzzle, you have to communicate. But if there is some way of doing it smarter, then you will reduce the communication. And that is the holy grail of distributed computing. And that's the holy grail of doing things right in Fluent. But the good, you know what is the good part? You don't have to do anything, because the code bit does it for you. But I just want you to understand this thing. When you make the mesh, the matrix partitioning takes care of this thing. when it divides up your computational grid, it minimizes the edge cut. Minimizes the edge cut. It reduces the total number of communications that happens within the processor. And it also reduces the number of different processors talking to number of processors. So you want to reduce the communication. You also want to reduce long communication. So you need to, even if it's a communication, you want to localize this. Complex ideas, not difficult actually to understand. But
Can I put this in a different example? Like, for example, there is a pack of cards and I have to segregate reds and blacks separately. But the reds and blacks are distributed to two processors, you know,
almost
randomly.
equally, almost equally.
Almost equally, but again, one doesn't understand does he have all red or black? But I just add another processor to it where it says that when red receives a black, the blacks are given to the third processor, and when the black receives red, it's been again dumped into the third processor.
Sure.
The third processor takes care of, you know, seeing where the red goes, where the black goes.
Yes.
Now this is a distributed way of
Absolutely, I understand.
multitasking.
This used to be called master-slave paradigm. So that's an old-fashioned way of doing it, where you say, well, I am the master, you guys just keep on communicating with me. What is the problem with this paradigm is that I am always the bottleneck, because everybody has to communicate. So that's a problem in every organization also, right? I hope nobody is listening to me. If you have to get your signatures done, even for your leave, all the way to the president, that organization doesn't work, right? And almost never it happens, right? Because you want to keep this thing as local as possible. The master-slave paradigm used to work if you are doing 8-node machine, fine. But now we are talking about 100,000 codes talking to each other. It doesn't, it has to be, so that the catch is synchronous. Everything needs to be synchronous. Okay, so again, now we land into a problem of domain decomposition. So domain decomposition is straightforward. On a picture on the left, you can easily divide it into 4 pieces. Fine. What about on the right? It's difficult. It will never be perfect. So you try to solve something, you get into another problem. That's life, that's research. So you understand load balance. You have to keep the load balance perfect, and then but there is only as much you have to do. The last slide, think of it, it's a very nice example. So now actually you understand MPI. Actually, you have probably never heard MPI, but now you understand MPI. That's how MPI works. The same programs run on every processor, but have access to different data. This program is going to run concurrently, but on different data. And then you have a mechanism designed that whenever you have a missing link, you talk to each other. Okay. So when I started doing it, because as you guys, if you have even done any programming or pseudocoding, the natural way of doing it is sequential way. That's how human mind works. I'll do this thing, stop, I'll do this thing, stop, I'll do this thing. Very easy to understand, extremely inefficient, right?
Fine.
Then you need to start thinking about MPI way of thinking it. And this example is very good example. Think of yourself in an island, right? You have a phone, you have a pencil. So you have a phone, you can talk to people. You have a pencil, you can record things. And you have a calculator, you can do some calculation locally, right? And you have a piece of paper with instruction, which is a code. Instruction, well, multiply this number with this. So this is instruction. Everybody on these islands, I mean, I would love to participate in that program, right? I mean, we'll get an island, we will be stuck there and we'll enjoy free vacation. And all we have to do is just run this code, right? And a piece of paper with numbers, data. So you have your local data, same instruction to everyone, and phone number. So when you have some instruction, say, well, multiply it with this number in this address space, I say, oh no, it's not, I don't have this data, I'll call some data. So that's how parallel programming works. That's it from now. We are going into hands-on session. Anything on parallel processing, any idea, any concept that is not clear, you can ask questions, and then I'm transition the slides. How many of you actually think reasonably confident that they can do a cavity flow problem right now on the workstation? Confident means I might ask the person to come here and give a demo. You think that you'll be able to give a demo right now?
Yeah, so you know, flow plug body like everything.
Yeah, you'll do that.
Yeah, I can do.
I'm out of business. I was not expecting that. Okay, good. So, who thinks that he has absolutely no idea? You're volunteering?
No.
And now the most important question is, where are the rest of you guys? You guys are doing it. So we're going to go step by step. What I wanted to understand is that how fast I have to go. I see that it will be useful. So I see some new faces today. So I'll go reasonably slow. Whatever time we have, we are going to spend on that till 12 o'clock, right? If you get stuck, I'll let you go at around 12, but I'll stay behind and I can help you. Okay, let's go. Let's get started. Remember, we are solving a partial differential equation, right? Engineers like maths, or you guys like math, or you guys don't like math? No, like that's typical. That engineers, whenever they're thrown some partial differential equations, that's not for me. But some, I mean, I think the different countries have different programs, so it's not universal. But I find mathematics as the only way to symbolically do a lot of things in mind, and not go to the nitty-gritty stuff. You're looking at partial differential equation, a Navier-Stokes equation, right? You can see domain. You need to have an idea of a domain, omega. That's where you are going to solve the problem. You need to have idea of boundary, how many types of boundaries there are. I mean, yesterday, Ajay explained you specifically in the context of fluent. These are special, so these are like hard-coded type of names, but generally mathematically, what are the two types of boundary conditions? Dirichlet boundary condition, Neumann boundary condition. There could be combinations there, but let's say these are the two boundary conditions. What is Dirichlet boundary condition? The boundary condition on the primary field variables. What are primary field variables? What you're solving. So what are you solving here? Three velocities and pressure. I didn't put energy equation. So let's say that's it. You're solving three velocities in 3D and a pressure, four unknowns, right? So any boundary condition on these variables would be Dirichlet, and then you have a Neumann boundary condition, because you see that's a challenge that Ajay was mentioning yesterday. So you specify a Neumann traction-free boundary condition. In traction-free boundary condition, you can see that the pressure is related to the gradient of velocity, because they're not same order. So there is a one derivative difference between pressure and velocity. So that's how the boundary condition of Navier-Stokes traction boundary condition, or the Neumann boundary condition, is written in this way. That's a traction-free boundary condition. Then, of course, if you have a time derivative, you need to initialize. You need to say that, well, initially the velocity is 0 or whatever. Now, you can get a unique solution for the given initial condition and for the given boundary condition. In principle, you can get a unique solution. In numerical world, we will never get a unique solution. When we see this problem, we just immediately say, we will never get a solution. We will never get a solution, which is a mathematically closed form solution for general geometry, generalized condition. So this is also called strong form of the problem. What is a strong form of the problem? Strong of the form of the problem says that I need to get a solution at every point. I need a continuous solution. I want to satisfy the solution at every point. That's a strong requirement from the solution. That's why it is called strong formal problem. We say, no, that's too strong of a requirement. Don't look at crazy maths. If you understand it, that's fine. If you don't understand it, just listen to it. The fundamental approximation that will take you into finite element and finite volume and all the numerical realization is the following. You say, I cannot solve strong formal problem. I cannot magically find that solution that will have zero error or residual is zero everywhere. All I can say is that in a weak form, I will minimize the error. What does it mean? It means that some point I will have a higher error, some point I will have a lesser error. So in the average sense, I will have very less error. So if this is a good enough requirement for you, I can get a solution. Now, if the mathematician in the room agrees to us, okay, yeah, I allow you to do that. Then we say, okay, that's how you do that. You multiply the governing equation with a weighting function and integrate. That's all. And that integral needs to be equal to 0. That is called weighted residual form of partial differential equation. So remember, Ajay was showing you integral form of the equation. So you didn't ask from where this integral are coming. Partial differential equation did not have integral form here. It's a discrete differential form. Why? That's how it came. We said over there that we are not going to find a strong form of the problem. We are going to find a weak form of the problem. We multiplied the governing equation with a weighting function and integrated. Now, the next question that you should be asking, if it is a for credit course, right now you don't care, is what is this weighting function? And that's the magic. Next slide is just going to, if you have these questions in your mind, next slide is going to really open your mind. Really open your mind. Okay, now I see some interest. Good. Now, I struggle with this thing. Here you go. If you change the weighting function, you can derive all these methods, right?
That's true.
Sorry? So if you have weighting function is equal to 1, that's finite volume formulation. That's exactly what Ajay was showing you yesterday. It was same Navier-Stokes, but it was integral written. There was no weighting function appearing over there. Okay, so that's finite volume formulation. If you have a direct delta, that cancels with the integral sign and give you a discrete formulation. That's finite difference formulation. If you have the shape function itself, that's a finite volume formulation. Okay.
A finite element, you mean?
Finite element, yes. Okay. Oh, so I have interest online. Good. So I'm not going to take you to SUB, GLS, and least square methods. Least square method, the residual itself is the weighting function. Residual dotted with the residual itself is a least square formulation. So it's a beautiful concept, actually. So I mean, people actually back 20 years ago, people used to write paper that this method is wrong, this method is right. But there was a groundbreaking paper actually 15 years ago. The title was Finite Element and Finite Volume to Good Friends. Don't fight. They're two good friends. So people knew, mathematicians knew back then, 100 years ago, that they're fundamentally same. So now you realize that they're fundamentally same, it's just a different implementation. Okay. So yesterday we did that discretization. Discretization is what? That few things in here. Let's understand this thing. By the way, this is a full course actually. I'm just giving you a simple idea.
So
first of all, you say that I have a domain. I want to discretize it, the domain, into finite geometries. Let's be general. Let's not talk about triangles or quadrilaterals or prisms. I want to divide it into finite geometries. preferably into a geometry that we are familiar with, cubes, tetrahedrons. That's just a choice. It doesn't, you don't have to do a particular type. That's a detail that, well, this type of element suits this type of numerical problem. These are details. In principle, all I'm saying is what is mathematical written. Divide domain into omega e element-wise domains, and union of that should be equal to the domain. That's all. All right. Then you say, it's okay. Was it alarm meant for me?
No,
That I should stop doing it? It's okay, it's okay. It's just. Then we say, now that we have transferred this problem into element problem. You see, we are not solving a global problem now. We are solving a local element problem. Now we have the luxury of exactly representing the solution, at least in the ideal geometry. Let's say the ideal geometry is quadrilateral element. Over there, I can, given the 4 solution, I can exactly represent my solution up to any polynomial, linear, quadrilateral. I can exactly represent this thing in the ideal quadrilateral. But if my actual quadrilateral is distorted, yesterday there was so many discussion on the skewness. If they are distorted, my ideal interpolation functions will not be exactly mapping onto that skewed element. So that's the error that you encounter when you have distorted geometry. On top of that, well, if your solution gradients are not aligned with mesh, that's a different thing. But that's a fundamental approximation that you're doing. You want your interpolation function to be exactly representing the solution. And here you're using a Lagrange interpolation function. You're representing your pressure field with the help of a 4-node Lagrange interpolation. Simple. Then after that, you do, remember, we have integral form. At the element level, we are just doing integration. That's all we are doing in any of the method. We are just solving integration. That's it. When you're building this AX equal to B equation, you're just doing integrations. There's nothing magic. We are not solving PDE. We are just doing integration. And over there, we are not doing an analytical integration. We are just using, you have done any numerical integration course? Yes, no, yeah, sure. Everybody did it. I mean, why you're not raising it? Everybody knows numerical integration, right? So you can do Gauss-Lobato rule or any numerical integration. You can evaluate that function on any number of points, and then you get exact solutions. There is a requirement. Yeah. Once you do all of this thing, discretization, express your solution in with interpolation function or linear function or shape functions or interpolation functions, and do the numerical integration, you'll end up with AX is equal to B, linear solver. That's what I was saying. That's the only thing that takes time. Rest of the things are straightforward, actually. These are just simple function evaluation. At the end of the day, you are just solving AX equal to B. I really don't want to go into this discussion. If anybody can volunteer and say something about stability, consistency, and convergence, then I can move faster. But it's really important, actually, because you will be solving a problem in Fluent, and you will be talking about convergence, but you're talking about a different convergence over there. What is stability of numerical scheme? Let's go. What is stability of numerical scheme?
If the scheme is producing, I mean, something is not growing.
Error is not growing. Yes.
Yes. Then it's not
That's
unstable
good.
one.
Thank you. So the gentleman said that if your error is not growing, that's stable. That's a posterior way of explaining stability. Posterior. What is posterior way? You do the simulation and then you talk about stability.
Okay.
Why do you want to do that? We want to do a priori analysis of
before,
right?
yes.
So a priori way of doing stability is that you look at your discretized formulation and look at your energy, and you do the error analysis. Error analysis is going to tell you that your functionals are bounded or not bounded. So fundamentally, when you discretize your formulation, you know that in the ideal setting, is it stable or not? Now, this is not talking about current number or time thing. This is just the space variable. Stability. If you numerical solution scheme is stable, then you go to next level. Otherwise, you don't do anything. If you're not unconditionally unstable, you don't do anything. You don't solve it. Then you go into consistency. What is these are difficult. If you have not done any numerical analysis course, you will not see this thing. Consistency is that you have your partial differential equation, you have your discretized equation. Discretized equation, Ajay mentioned yesterday. You just take your derivatives, put some shift linear functions, you get algebraic equation. These two should have one-to-one correspondence. If you approach delta x is equal to 0 in the discretized formula, it should approach your PDE. What you cannot do is that you discretize your partial differential equation and say, it doesn't look good, I add one more term here. That's the upwinding scheme, infamous upwinding scheme. People just added a term over there because it helped them with stability. You cannot do that if you want to be consistent, because as you refine the mesh, you will not get to your PDE. So that's consistency. Convergence is something that you understand, right? As you refine the mesh, you get to the closer to the exact solution. As you refine the mesh, you should be converging to your exact solution if it is not. Again, if you can handle infinitely large mesh, in principle, you can always get a converged solution, provided your problem is linearized or piecewise linear, and all those nice things are there. What are the solutions? You can write your own code. Yesterday, Ajay was preaching for that. Almost nobody does it these days. It's in the MBI setting. It's very, very difficult. Either you use some libraries, you interact with libraries, you write some Python program, you interact with libraries. That's how people do normally. OpenFOAM is one paradigm. There's another. There are many. Or like you guys, you're just going to use third-party codes, right? So right now in this setting, you're just choosing a third-party code, which is a Fluent, right? And we are going to solve this problem. Okay. What is this problem? It's a cavity flow. Anybody who does not understand cavity flow, I'll need one volunteer, otherwise I'll just go ahead. Oh, good. So you don't understand cavity flow. So it's a 3D structure, right? And the top wall is moving. So if it is moving with some velocity, it's going to give rise to shear layer. So there will be shearing, and then there will be a recirculation in there. So what is the applied importance of such flow? Any natural phenomena that resembles this type of thing? Yeah, tornadoes, hurricanes. Yeah. So if you handle this problem nicely, well, you can model those shear flows. This is a last descriptive, and then we go into the workbench. That's how you interact with supercomputer. You really need to understand this. Yesterday you learned, or day before yesterday, you learned how to model your geometry. Then you learn how to mesh it. By now you know this, right? I assume that you know. We'll go over it again. Once you have your model ready, you can run it on your workstation, or you can copy this data on a supercomputer, get your solutions, and put it back on your workstation. So that's a cartoon that it is showing. Not very difficult, and we'll go through this thing right now. So if you can open your workbenches now. I should have asked you to do it before to save time. Okay, Step number 1. Okay, I need at least one volunteer who will be working with me. So I'll just get that confirmed. A person who thinks that he will be a slower than others. Any volunteer? You're volunteer for pretty much everything. Okay, I really like you. Okay, what's your name?
Mine?
Yeah.
Perfect. Perfect.
Okay, so everybody should know this name now. Turkey, did you drag Fluent Flow here? Done?
Yes.
Cool. Let's go. So let's edit geometry. So I'm not fancy like a Wasim. So I'm just gonna do old-fashioned way, design modeler. Open design model. It's gonna take a few seconds. Well, I try to do it extremely simple. Probably nothing can be more simpler than that. But there are some advantages to that. Design model is open. Anybody having problem with opening the workbench? No? Design model is open? Yes? No? Click on the XY plane. You can see the cursor. Online friends, you might have trouble following my cursor, but I'll try my best. I click on the XY plane, right? Turkey? No, you need to tell me.
Okay.
Yeah. Now the next step, new sketch. You can see this picture over there.
Yeah.
Click on it. It's a new sketch. Good. Go to the sketching. Click on the rectangle. Go to the center and draw a rectangle. Done? What's the next step? Did we cover dimensions? Okay. Click on dimensions and take the cursor here and do these things. So I'm gonna, well, since Turkey is volunteer, I'm gonna help only. Okay. Anybody who has not done this thing? Oh, you need help? See? All these commands, I'll send you these commands. Okay. I should not be showing my cheat sheet. So you guys are with me? So let's put one meter and 1 meter in these dimensions. All right. Press generate. Don't forget to generate things and then make it a little bigger. Oh, generate is up there. Okay. All right. Now we go into face extrude. Can you see extrude? Extrude, right? Extrude, and the depth 1 meter. It's already 1 meter. I'll put 1 meter again, and it's gonna make a cavity. After every important thing, you have to press generate. Generate. Once generate is done, you will see one part, one body. Are you guys there? This box in front of us. This is our cavity, right?
But mine isn't centralized, well, isn't going around the screen.
Oh, because when you picked when you were making a rectangle, you're not exactly at the center. So probably doesn't matter. Let's just go with it. Anybody who needs help right now? I really want you to actually go through the whole thing. Otherwise, no point. Yes, where are you?
So can we do this in space claim too?
Yeah. Because we can change the dimension 1, 1, 3, that's fine. It's fine. All right. So what all we have done, remember the mathematics that we went through? We have defined our omega. This is our domain. We defined domain. What next we have to define? Mathematics. Boundary. Oh, how many faces there are? What type of different boundary conditions there are? Two. Fantastic. One is the moving, one is the fixed, right? Both of them, they are Dirichlet boundary condition or normal boundary conditions. They both are Dirichlet because it's on the primary field velocity. There's no traction bounding. This is internal flow, so it's all Dirichlet problem. Very well posed problem. That's why it's a classical textbook problem. Good. So let's put this. We are not going to put the boundary condition right now. We are just going to identify the planes. And it is to our advantage that we identify it in a way that, well, two type of boundary condition, let's combine all the faces into each class. So we'll define the top differently and the 5 others differently. It will be tricky with the cursor. Let's see if we can do it or not. All right. This is a very, very tricky part. So look at these things here. So if you go here, it's a selection filter faces. You have to click this thing. If you don't do this thing, and if it is you do it twice, it will be a problem. So it has to be in this way. It's very small. I apologize. Well, but that's all I can do right now. Can you see this thing? Yes. Then you go on the top face, click on this thing, it will become green. Are you green? Are you rich? Right mouse button after this thing, and you'll open this thing. Name section and put a name. Whatever you want. Moving. Are you with me? Yes. Oh, yeah. A name is totally arbitrary. You can say, you can put any name. And then press generate. When you press generate, you'll see a moving thing on the icon. So I want to see moving in your legends. Yes.
It is resolution, that's why. Oh, okay. It is 1 by 1. Okay.
So, but it's not, it's different. You find it? All right. Anybody needs help? No? Very soon we will get into a point where I will not be able to help you. Because the geometry, if you make the geometry right, next things are easy. If there is a problem here, I will not have time to come back. Okay, get it done or ask for help. Wasim is here. All right, now it's a tricky mouse business. So I'm going to go into again, this is active or not. Is this the right way? This thing is active. I see, right? Now I'm gonna go and click on this guy, put the control button, click on this guy, and then look at the maneuver. Be very careful. I'm going here. Can you see? I click here and use the cursor to go here so that I see. Now I'm sorry. Oh, I cannot. I'm in a very difficult position right now. Okay, let me go back again. So if you if you get stuck, this button is your savior. It's going to bring the view back again. Okay, you selected two side faces, yes or no?
No.
So you select two faces that are right in front of you. Press this rotation. I'm sorry. I'm sorry. Yes, with the same selection. Yes, we want to branch them together. Now I'm going to put this.
Do we need to select the two faces for the movie?
No, just one. Just one. Okay. Now I'm going to rotate this guy and go behind. All right. All right. And then I'm going to untoggle this rotation button and put control again and do the click here, click here, click here. And then right mouse button, and I name this thing fixed. Okay, and then generate.
How many places down there?
5.
5 places. Yeah. So,
Okay, so let me show you. This is my moving face, and this is my fixed face. Moving, fixed. We are basically done with this thing, but I want you to be there because if you fall behind, right? I thought that 1.5 hours is enough. I think we should have more time. Now I should have more time. Yes. I'm sorry. I'm sorry. Yeah. So okay, here is what I propose right now. What I propose is that, well, I know somebody might have pressed something wrong and they're falling back. That's fine. So at least on your row, if you can find someone who is doing something, team up and follow me. Otherwise, I mean, we are going to fall. We have to give a test at 12:30. So there's some limited time. All right. Okay, now I have defined the boundary conditions. What else I have to do? I have never told this guy, software doesn't have brain. We have done everything. We never told him that or her that we are solving Navier-Stokes expression. He might be thinking that we are solving elasticity problem. So what do we have to do? We have to define that somehow that we are solving fluid problem. So let's see how can we do that. It's simple. We go into the one body, click it, you see solid. By definition, by default, it says, well, you guys are solid people. We are solid people, but we want to solve fluid problem. Okay, fluid, and then go here and select fluid. The moment you select fluid here, now they understand, oh, Navier-Stokes. Let's do everything internally about Navier-Stokes. Okay, generate. All right. If everything is done right, we are done with geometry. We export,
Sorry.
we export,
File.
file, export. Wherever you want to do that, desktop is fine or wherever. Desktop, and then you can name it 𝐀𝐍𝐒_𝐔𝐒𝐒 or leave the extension as is. I save it.
Okay.
Now I'm closing modeler. Anybody who wants some help at this point? Okay. I'm closing modeler. Okay, what do we do next? When we go into the workbench, we see geometry is checked now. Good. We go into the mesh, right mouse, and edit. Edit meshing. It's going to open. Okay. Yeah, it's going to take time because you see starting meshing. So now you see this thing. Okay. Are you guys on meshing? Anybody on meshing? Are you on meshing? Yeah. Okay. So you can see that. So at least in one row you have some. Are you guys fine? Anybody who's doing fine here? Oh, fine. Oh, we'll go slowly. Okay. Oh, you're right. So you have one. You can at least follow. Where are this is your first. But you might have saved it in a different place. Where is it? That's not one. So then we need to point from here, go to input. You make this. Oh. So can you try feed time on that? All right. Meshing. Let's do meshing. So here is the fun part. You click on mesh, and then you define element size. Mesh. You clicked on mesh and go into the element size. What do you want to put here? I'm sorry? Size, but what is your idea of size? What do you want to put? 100, 2, 1.01, 0.001. What are you thinking before you're doing it?
No, it's not less than one.
Less than one, but what you should be considering here? Yes. Yes. So what should be the driving thing? What are you solving here? What is your Reynolds number? What will be the velocity on top? Higher the Reynolds number, smaller the mesh size should be. So all those type of things. Right now it's a cartoon problem, but all of this thinking needs to be there when you're making the mesh. And on top of that, you need to refine the mesh, maybe not uniformly. You might want to go cluster it on the top wall because all the action is over there. Right now, I'm not doing it, but just think about it. Right now, okay, the online people put it as 0.1. In-person people put 0.01. Let's give more work to Shaheen. All right. Generate mesh. and wait. It's going to take some time.
Generate, huh?
Generate mesh.
Just general mesh, or we can specify the mesh.
We can do everything. Right now, we are not doing it.
Yeah.
We are making it extremely simple.
Why you have very small?
Because I put 0.01. What did you put?
Pick your life.
Element size, 0.01, 0.01. Generate mesh.
So now the height here is 0.01.
Yeah. Your length is 1, so you would have 100 elements per stretch. It's like 100, like 100 times 100.
Okay.
4 million elements. Yeah.
So at least I see few people here. Are we done with meshing? We defined our boundary surfaces. We meshed it. We defined the domain. We defined the physics. So far, so good. We are done with the meshing. But before we do meshing, let's save the file. File. Export. Mesh. Fluent input file. Export. Put the name, put a cavity underscore mesh. It's arbitrary, but well, I'll come back to that, but let's put it in the same desktop place. Okay, I'll do that again. Okay, so you have a help over there. You have local help. That's exactly what parallel processing was. If you have local help, that's more efficient. Okay, I'm done meshing. You are with me?
Yes.
You are representing everybody.
Yeah.
So you're responsible for it. So I'm just going to report everybody did what you did. So, yeah. So file close, I'm closing meshing. So we go to the next step, setup. Now you see mesh has some lightning thing in front of it. It didn't like something. I don't know what it is. So what I even don't understand what it is. But what I do is that I do go here and put update. So who is saying that? So you see, have seen this thing before?
Yeah.
Here's your experience. Your current user
Yeah.
or during this session or before that?
Before that, it was, yeah.
So you update. You update
Yeah.
and things stars are aligned.
And I don't ask why.
Me either, but I asked, you explained. Thank you. So that's a thing. When we are in the software world, logics don't make sense. It's just a pressing of a button, right? Maths, there's no maths there. If you're stuck, you're stuck. So yeah, no amount of IQ is going to help you if you get stuck in these things. So let's not get stuck. And let's be all together. Okay. Yeah, we are done with this. So when I update it, I get a check mark. Check mark is good. Okay. Now setup, edit setup. And wait, while it is loading, I think I need to set. Okay, this is really important. 3D, you always have to press double precision. There is nothing in CFD that is single precision. If you're doing iterative solver, single precision will give you nothing. So they used to say that experimental people who never liked CFD people. So back in our time, they will say you put garbage in, garbage out. So if you put garbage input in, always the solution is going to be garbage, right? So wrong inputs, wrong output. So never put a single precision here. Don't display mesh because it's going to make life difficult. Don't do that because it will be slow. So don't do that. So start. Okay, while it is starting, what do we have to do? We have to set up our boundary conditions. We have to initialize. We have to look at the material properties. We have to look at the solution, solver, steady, unsteady. What else? What else? Turbulence. Is it turbulence model or not? What type of turbulence model? What type of numerical scheme? Yesterday there was a beautiful discussion about third order scheme, second order scheme, all of those type of things. That is what's going to happen now. Okay, I think it just cancel, and it works. Just don't. Okay, yeah, I think I don't know. These are one of those things that nobody has answer to, but we just do something and it works. Okay, so if you guys are falling behind, no worries, just follow this thing, and then I'll give you typed things. You just repeat it. Everything you'll be able to do. Then just follow with me. Then use it as a demo, not a hands-on. But if you're at least 5, 6 people or 10 people are doing hands-on, awesome. Do you have a question, sir? Okay. Yes.
So which
Okay. I don't know at this point. No, you become like my. Just follow them, and then we'll work it, because we really have limit time. All right, folks, attention. General pressure-based solver density bets. We are doing pressure-based solution, steady state, unsteady. Just click steady state. All right, models. By default, it is doing SST 𝐀𝐍𝐒𝐘𝐒. It's fine. If you have reasonably high Reynolds number, let's be it. That's fine. Turn off multi-phase. We don't need any of all the things. Models are fine. Material, fluid, it's air. Let's look at the properties. It's air. These are the density and viscosity. We're fine with that. We like air. Okay. We don't want to do anything here. Cell bounding condition, boundary condition. These are the important things. Boundary conditions, internal and wall. Wall, double click. These are the two walls that you set it, right? Moving wall first, double click. Moving wall, right? Put the velocity here. When you're going to put the velocity here, you're going to set your Reynolds number, because your density is fixed, viscosity is fixed, dimensions are fixed. 1 is a high Reynolds number. If you put 1 meter per second, which is very small velocity, it's a high Reynolds number. Let's see if we can solve it or not. Let's see. For online people, since you have done 0.1 in the dimension, change it to 0.01 meter per second, please. Apply. Okay, close. Let's look at a fixed boundary condition. Pretty much nothing needs to be done over there, but let's just take a look at it. Stationary wall, nothing, no slip, fine. We are fine with that. All we have to do after this is, these are method details. I don't want to go because we don't have time. Defaults are fine. I'll be happy to go into the details, but defaults are fine right now. And then initialization is important. Initialization, hybrid initialization. Initialize. Then you're done. Okay. Yes. I don't know what is inside it. I don't know. It's a fluid specific thing. Wasim, do you know what is the difference between standard initialization hybrid? If not, what I think it is, don't quote me on that. I can confirm from a minute. Standard initialization would be, if you want to write your code, what is your initialization? You say, okay, start from 0. You have velocity field and the pressure field. You say 0 velocity and 0 pressure. Hybrid would make it a bit more intelligent initialization, so that you start at a better initial solution. So the challenge is that if you give a better initial solution, you will have less iterations to converge. So what you can try right now, not right now, after that, is that you run a solution with standard initialization and hybrid initialization and plot the convergence on top of each other. My guess is that for this is a simple problem. Both will be same. But for complex external problem, the hybrid initialization will converge faster. That's all I can say. No, of course not. Initialization, is an for steady state problem. Initialization is arbitrary. You agree with me? Steady state problem, initialization is not important because your time dependent term, it doesn't matter. It is just temporary, it just marches you to a steady state. No, if the schemes are convergent, consistent, blah, 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 all those things are right. You start from any arbitrary initial solution, provided you are convergent, you will get to the unique solution, unique numerical solution. But it will matter in unsteady. Obviously, unsteady solution is for a given initial condition. I gave you a long explanation, but it was important. Sorry. Okay, all we have to do is export this thing. Export.
Can you show about methods?
I'm sorry, there is an online question.
Yes, sir.
I didn't get your question.
So what methods we have used? Is it coupled?
We just left all the default methods.
Okay, sir. Okay, sir.
We didn't change anything. All we did
Okay,
was set boundary condition and the initialization. That's it.
Okay, sir.
Export case file. So now you are exporting a case file. So for again, for unknown reasons, every time I try to export a case file, some weird things appear here. I have to do this manual editing. I don't know what, is it just me or? And absolutely no explanation for that. I don't know. So a case file, I need to put the path. I'll go to desktop and then I'll name it 𝐀𝐍𝐒.case. All right. Okay, it's going to write the case file.
Not assign any report.
I'm sorry.
It is not assign any report on the surface. The report definition. So you did not assign any of the report definitions.
No.
You don't need to monitor any of the.
We'll just look at the conversion. We'll have solution file and we'll look at the solution. All right. If everything is done correctly, wherever you are saving this thing, Wasim, could you please do me a favor? Start telling the online people that we'll be a little late with the exam. We'll announce later. Okay, because probably we'll take a bit more time here. Yes. I'm sorry. That's fine. No worries. Anybody is free to drop out anytime. That's fine. No worries. But all the material will be with you, so that's okay. Okay. If everything is done correctly, we should have 3 files on the desktop. I find it difficult to reach there. I have so many things open. No, I don't want to sign out because it's gonna mess up everything. This I can close. I can close this thing. No, I don't want to end all the meetings. Okay, I'll minimize it. This is fine. I'll minimize this thing.
Yeah.
So I have this file, and there should be another file.
Yeah. What the last diagram in the second column. Yeah. Up. Yeah.
Oh, okay.
Yeah.
Sorry. It's so that yet another unexplained thing. Okay, we have I have these 3 files now. What do we do now? Now Shaheen starts. So your Windows, you need to copy this file, the case file. All you need is a case file now. Other files are not important. We've saved other files just to have a good restart. For example, if you want to make another refined mesh, you start with the geometry, refine it, and make another mesh file. So these are important. Right now, just case file is important. So you have to copy this case file to Shaheen, run it over there and bring it back. Okay. So in order to copy this file, you need a git bash tool, which we already downloaded. On this screen, you do git bash. No, not GitHub, git bash, this tool. So you click on it. You'll see this thing. Not a very charming thing, but well, that's what it is. Okay, by default, I am on a P, but I need to go to desktop. How do I do that? Okay, Windows folks.
Every year change drive.
See,
Yeah, you should go like 𝐀𝐍𝐒𝐘𝐒 user.
anyway, I have data. So you guys know how to access your P drive. You put everything in your P drive? No, I'm asking you. Where did you put everything? No. These file, the case file, where you have right now? Desktop. So can you go to your desktop?
CD dot CD dot. Okay. Okay. CDC. C. No, just C. Just C. Okay. Dir. Okay. Now users. Okay. Then your desktop.
Oh, thank you. Okay.
DOS.
That's DOS.
That's DOS.
So on your P drive, you do CD capital C, then CD. So you can see the command over there. Then you do CD users, your username and desktop. Anybody on your desktop now? Or not? I cannot. It's
So do we need to download
Windows.
Bash? So do we need to download Git Bash?
No, no, you will not be doing on Shaheen, so online people. So you can just run it on your workstation actually. So it's bigger, right?
So online people just have to view.
Yes, yeah, for now, yes. You cannot access Shaheen, sorry.
Okay.
Are you guys on desktop?
Are you in the desktop now?
Are you on the desktop? Are you on the desktop? Let You're done? That's your user history. So you have all the file on the desktop? You are. Or you're fine. Okay, so who needs help? See, a simple task of so Linux. Yeah. You guys don't like Linux. Okay. All right, so let's get started again. I think we have sizable amount of people doing on desktop with the file. Can you open another Git bash terminal? I want two. One where you are on desktop, another one. Git bash. So next time we need more time for this. Again, go to, on the second terminal also go to C:/CD user, your username and desktop. Okay, I want two. I'm sorry. I don't use the size. If I do that, I'm going to the problem. I can have you big plus all right, now I need your attention as if you are not attending, giving attention at all. So now I want you to connect to Shaheen. Remember all the ritual that we did? Don't tell me you forgot your number. I actually forgot number. I'm going to use 30. Okay, don't come to 30. And you remember your number. Do you know what to do? So here's the command. You can see the command, right? Do this thing. Yeah, both are on desktop. It's fine. It's bigger, but I don't know how to. Okay, yeah, here it is. That's better. Okay, but I don't see the. I cannot see the other thing. That's the thing. So it's better for you, not for me. Okay, but let's see. Okay. It's Windows.
Just reduce the size again. If you reduce the size again, it's gigantic.
Yeah. I don't know how to do that.
Sorry?
I don't know how to do that. Okay, here.
Exactly. So open this one. Open whatever you like this. Yeah.
Yeah.
Just you can press this one and just you can control Z. So you can increase.
Okay.
So we can.
Perfect.
The password was not working.
Okay.
Should we put yes or no?
But what?
You need to ask you something, yes or no? Then you start with your own continue connect.
Yes, press yes. It's not.
Password didn't be- we need to transferize storage. Yeah, for some reason, it's not working. That one is not working. That's right.
It's not working.
No. I try also PSL tracking 2022. Just this.
Yeah.
One time for blah blah blah. But we should like what?
Okay. Let me tell you what happened. Yeah, I understand. So they only allowed us the window from 8 to 12. So because they cannot give us in longer window, we expired. What we can do from this time is that let me give you a demo from my own account. You are here. All you have to do is one command, SCP. If you do this SCP command, you'll take the data over there. Now let's assume that you have done it. I have this file on Shaheen. So is it fine if I show you just a demo?
Sure.
You will go back and thinking, well, that's not exactly the same. We can do another hands-on session some other day, but let's do that because we are running out of time. Okay, so let me make it easy for you. So let me do that work, okay? Yeah, your number, but I think that is not working. It's expired. Yeah. But no, it will not work for you because you don't have a standard account. Oh, you have a count, then you go, you can do that.
Did you change the password?
I'm going to my own account. I'm just giving a demo. Okay, folks, I am on Shaheen. All right, just give me some attention. So right now, we have a gap. So you created your case file. There's one magic command, SCP. It's going to bring the file to Shaheen, have it in my account. After that, whatever the steps are, let me show you to you. So that's the best we can do right now. All right, I am on Shaheen right now. So I go to scratch, CD, scratch my username, and I have a 𝐀𝐍𝐒 demo here. Just to tell you that, oh, I have been working. You guys made me work. So I have a backup just for these days. I have a backup solution ready. Remember this file. This is important for at least one user who actually wanted to see this thing. This is the file that you created, right? This is the file you created. You are more expert than I am to create this thing. So that's, you know how to do that. I'm not going to tell you how to do this file and copy it. Now you have this file. In addition to this file, you just need 2 files, and then you are off you go on Shaheen. What are these 2 files? One is a journal file of Shaheen, and another is a Slurm job script. What is a journal file? Remember on the GUI, what did you do? You make the mesh and you put run. Just it starts running over there. Here you cannot press run. You have to write some commands. So iterate, do something. So I will show you that command. You don't have to change. I'll provide. All these files are already in Shaheen. I'll provide you file. And once you have that file, you need a Slurm job script to submit your request to supercomputer that, hey, there are so many users. I have a request. I want to submit this job. Whenever you get free resource, run this job. And once you get this request done, it will run your job and give you a solution. Not difficult. In addition to case file, 2 files, journal file and the job script. Let me show you very quickly what this journal file looks like. So this is your journal file. Extremely simple. It says, read this case file. Again, subject to if you change the file name, you can edit these files. These are simple. Iterate it for 1,000 iteration. You can do it for 100. You can do it for million, no matter what. And then save a solution file. That's it. Rest of the things are commented out. All right. As simple as that. Just for steady state, you can use this job script in journal file for everything, which is steady state. For unsteady state, it's a little different. Don't worry about that. This is clear, right? Now you have a job script. What is this thing? It says, Shaheen, I'm asking for 2 nodes for 10 minutes. The job, my job name is Fluent. Rule already installed everything. I'm just using it. I'm not installing anything. Everything is there. You just load the right module. That's it. And you just run this command. That's it. So what is this 64? 64 is number of cores that I want my job to run, because I asked for 2 nodes from Shaheen. Each node has 32 cores. I put 64 here. Now, very difficult question. If this is 4, what do I put here? You just have to multiply it with 2. Here you go. So that's all you need to understand. So if you understand this thing, now you can do strong scalability, right? You have the same case file, you change the number of node and number of minus t equivalently, and you keep running the problem. And
Each node goes 36, 30, 32 core.
each node has 32 core on Shaheen. Yes. All right. You are with me? That's it. After that, the magic will happen. Let me remove the unnecessary files. Slum. So then you do sbatch job.sh. Okay, all these commands are in the handout I'm going to give you. Don't have to write it. Just follow me. So it said, I have submitted your request. What does it mean? Is it running? I don't know. So what do we do? Here you go. Let's check. SQ minus U, my username. Oh, it's already running. Its status is running. So we are good. What do we do? Let's see. What is the output file? Tail minus F slam output file. So there are some warning messages. Don't worry about that. So it's reading the journal file. It's reading the mesh. You see Mates, Parmetes, all these things that I was doing, it is doing for you. You don't worry about it. Now you start the solution. It's doing solution just using 2 nodes. All right. This is pretty much similar what you experience on your GUI, right? It gives you similar experience. I'm not happy with this. I'm greedy. So what do I do if I want more from Shaheen? I go and I do exactly the magic math that you guys did. You multiplied everything with 2. Let me do that. Okay. So I'm just trying to give you that. Well, will it run faster or not? So SQ, is it still running? No, it's completed. Okay. What's the situation? The solution says that, well, in 37 iterations, Fluent converged. That's fine. And there's some parallel statistics here. It says that 25 seconds were spent on these 37 iterations. Okay. So I already converted my input file to 4 nodes. Let's see. Do you expect it to run in 25 seconds now or not? Think about it. Now you are mature. You cannot answer this question. It's running. So I'm just using this time. You cannot just answer it without thinking. You have to think, how big was the problem? Is it big enough for 128 core or not? How big was the problem?
1 million.
1 million?
1 million nodes.
1 million nodes.
1 million.
0.01, 0.01 in each direction. 1, so 100 by 100 by 100. So I just put 1.01 over there. So is it big enough? I don't think so. Not that big, yeah. So I'm not expecting some magic here, but let's see what happens. So at least let's see if it is running or not. So it's still running. By the way, while it is running, now you're practical. Now HPC sales pitch is finished now. You're practical people. So something, if you run only for few iterations, there is an overhead that you have to do. If you increase the number of processors, the partitioning will take more time. So if you have to run for 10,000 iterations, the only speed up happens in the iterations, not in the setting up, reading a file and all those times. That's an overhead. All right. So let's see if it is still running. It's finished. Now, what do we expect here? We had 25 seconds over there. I don't know. I frankly do not know, because I think the problem is small. Oh, you got it? So it's 12 seconds. So Fluent proved me wrong, totally. It said, okay, it's not big enough problem, but I'm good enough to scale it. So Fluent is better than what we are giving it credit for. So from 2 to 4, it reduced the time to solution 1/2. We are done now. Let me show you one. So I did a lot of studies actually, because I ran the full scalability. Then I got greedy. I said, okay, I didn't do only this thing. I did all of these runs. Not only that, I went to 1 million was small enough. I created a cavity for 8 million and 64 million mesh also. I could not go to 128 million because my workstation choked. So these are the practical things that you have to face, because supercomputer is amazing, but you have to make mesh on your workstation. So you have to use some of the tools that Wasim and Ajay was telling. You have to do some automatic refinement on the Shaheen. That's a limit. And then there was another limit. So there was another limit. I actually liked whatever we achieved so far. Let me directly, so this is fine. Once you do everything, you go back and copy the solution file back, and you will see these results. You already know how to do this thing. Any question about how to visualize it? That's straightforward, right? You go to Workbench and go into the solution, and then you can put a section, and then you start looking at these results. They're fine, they're good. But this is important. This is the last slide. This is important. Now, take a minute and try to understand it, and let's discuss what it is. So when will I go on the right? Why will I use 64 million mesh when my Reynolds numbers will be high, right? So you need to have some idea that this is my Reynolds number. I need to have some mesh like this, and I'm a solving turbulent on, right? So your mesh will be determined by that. Then you need to fix the right number of core count for that. Should I run it on 1 node or 1,000 nodes or 2,000 nodes or 6,000? China 6,000, 200,000 cores, right? So look at 8 million scalability on 2,000 cores to 4,000, almost scale perfectly. After that, it stops scaling. That answers some of the questions that we're discussing. Why it stopped? Why it cannot be worse than that? No, it can be worse than that. If you go on further, it will be even worse because it stops scaling, right? Still 64 million mesh kept on scaling. So I was greedy enough to go essay 8,192 cores is not enough for me. I want to go to 16,304. What happened? I do not have license for that, right? So our license is limited to 11,000 core. So these are the practical problems. So you need to understand where in this parametric sweep your problem lies. What would be the right problem size? What would be the right core count? If you do, this is the exact work. There was a discussion here. This is the exact work that you are supposed to do in your development allocation. Once you do this thing, after that, you're going to say, I've done everything. No, this is my typical problem. This is the typical problem on which I'm going to run my production run. These are runs done only for 10 iterations because every iteration will be repeated. So scalability study can be done on few iterations. Any questions on that? I'll give you 30 minutes and we will probably give exam at 1 o'clock, but I'll stay here. If you have questions, I'm sorry, I will go a little extra, but I hope that.
Thank you very much, Dr. But if you can please just give us the instruction on the exam, how does it run and what
So
should we?
instructional exam, nothing. So just have a nice lunch.
Coffee, okay.
If you want to pray, eat, relax, and nothing. So it's multiple choice questions. And then I think, Wasim, have you seen it? It's probably 45 questions. And then you will be given 45 minutes. Oh, no, 90 minutes, 1.5 hours. And then you'll be able to upload it before that. Don't be late. don't be late beyond 230. Can you tell Julia that and Philip that don't deactivate at 2
Is it
Deactivate
something that
please.
yeah, are we
Yes.
are we downloading and then working on it and then
No.
uploading, or is it
just keep
clicking on
visiting the website. There will be a link and everything is self-explanatory.
okay,
Thank you.
okay. So
I'm sorry.
so this is going to be
I
at,
think so.
2 o'clock in your time.
But I have
I
not
mean 2
given
o'clock
that, so
2 o'clock in
doesn't
my
matter.
time.
So I'll give them 2:30. On yes, question.
How do you know that someone is already using all the
Oh, that so you have two things to know. One thing is that how many people are using Shaheen? That's also important because that's a second thing. First, you need to know how many people are already using Shaheen. So you do as info, it will tell you how many nodes are free right now. That's one thing. I know, I'm just getting to that. So that's first thing you need to know. Second thing is that there's no way to find out. You just run it. If somebody else is using, you'll get an error. So I got error. I ran many cases. So for example, if you run 2 cases of 8192, if first run is running, second run will fail, right? Because in total, you cannot exceed 11,000. So in those cases, I run these jobs with dependency. So I'll tell you, you can have a private time, how to run 10 jobs with dependency, because dependency is because you cannot exceed this license limit. So dependency says, run first job, when this job finishes, launch the second job, launch the second. So if you do this thing, you can go back on vacation and come back with it. Does this answer?
Is it like dependency or like there is only one, let's say there is only one core available, the system runs on that particular one core, and then if there is, in the meantime, if a second core gets available.
No, it's not that.
It's a series.
No, dependency makes the workflow serial. That's exactly.
So is it possible to make it in that sense, like the
Yeah, what you mentioned is a scheduler is already doing it. If you want to run 5 jobs, you just submit without dependency. The first job will get submitted, and the second job is looking. It gets submitted. So you get your own priority because you're submitting more jobs, and then each job will get different priority, and they will get some.
That is also.
That is exactly the job of scheduler. Job scheduler does.
One more question. When you said that when you executed the command to run the file, okay, check the status of the file code R over there. What if it is the queue? What
So it will show.
the queue or over there, or
It will be held or in queue, or it will be some method. That depends on the scheduler. It's a Slum scheduler, every scheduler has to do.
I would like to go.
Yes. There was a question.
Yeah, as I said, I have an appointment. Like, can we start the meeting now, or I can? I can talk before. I will get these things.
I understand. I don't know how to do that. If I open this thing, there, everybody on the online will do that. So one thing I can suggest is that we can do this example.
Next one.
I will open it. When I'm done with this question, I will open this test right now. But I have to answer the question. I see, I'm not parallel. I'm serious. I can only do one job. So that's a limitation. Yeah, but questions are important. Whenever I'm done, I'll just put the link over there and you can look at it. Questions?
This time is in seconds.
But these are only for 10 addresses. Only for 10. Because we don't want to run it for 1,000 addresses because they are repeat. So even 10 is just for getting a good status. One is also enough, but one small time, reporting time in computer science, we don't like milliseconds. It has to be few seconds. These are repeatable. Online friends, the link is active. You can start the exam whenever you want. It will be deactivated at 2:30 p.m. Good luck. And that's all from us. Thank you.